Nielsen model is the model we go to first, and quite extensively, to understand the behavior of deformed odd mass nuclei. So you can think of it as a deformed independent particle model. And the way we use it, in fact, is even simpler than for spherical nuclei. We use the independent particle model plus residual interactions. The Nielsen model, in a sense, is used in an even simpler way. So I want to describe that and discuss some aspects of it, including Coriolis mixing. And so since in heavy nuclei, most heavy nuclei are deformed because the shells are big, there are lots of valence nucleons, recall again the P factor. If NP and NN can get large, this will always be greater than 5, which is kind of the boundary between spherical and deformed. So in heavy nuclei, you always get these regions of deformation, and so it's pretty important to have some model, some independent particle model for non-spherical nuclei. And that's what the Nielsen model is. So just to start the discussion, we're going to limit ourselves to nuclei that are axially symmetric or nearly so. The vast majority of nuclei of deformed nuclei are very close to axially symmetric. You remember this parameter gamma, which can range from, in one convention, 0 degrees for prolate deformed nucleus to 30 degrees for axially asymmetric, maximum asymmetry to 60 degrees for oblate. In most deformed nuclei, gamma is between 0 and about 12 or 13 degrees. But the change in structure as a function of gamma is highly nonlinear. So that most of the change in structure of a nucleus as a function of gamma happens between 20 and 30 degrees. So for nuclei where gamma is 0 degrees, 5 degrees, 10, 12, even 13 or 14 degrees, they behave very, very similarly to axially symmetric nuclei. So I'm going to make that assumption. It simplifies things. So the question is, so here you have a nucleus with a symmetry axis Z. It can rotate around this axis, okay? And notice that's perpendicular to Z. That will come in a moment. And the question is, what are the, oh, let me get rid of the lights. Now comes something very dangerous. I've got to get to the light screen. Okay. So the question is, what are the energies of particles in orbits in such a nucleus? What are their wave functions? They somehow will have to be different than in spherical nuclei. What new features enter, and what about residual interactions? Those are the questions we want to kind of address. And it's sometimes useful to give physics a personal aspect. So I was thinking of this coordinate scheme, and I was thinking of something we saw on the tour, and there is Navin simulating a coordinate scheme. Whoops. So there he is. This is the z-axis. He's going to rotate about this axis. Anyway, so now you understand coordinate schemes. Okay, so here's the answer to the question. This is the answer to the question of what are the energies of orbits of particles in an odd mass deformed nucleus. Okay, now, how many of you have seen this diagram? Most of you. How many think it's complicated? Okay. How many would like to find out that it's very simple? Okay, good. Some of you don't seem to care. Okay, so I'm going to try to explain this diagram and a couple of features to notice. So what the diagram shows is this is deformation here. And instead of beta, I use something called epsilon. I'll comment on that in a minute. This is epsilon equals 0. That's a spherical nucleus. So these energy levels here are nothing more than the independent particle model levels. And here you have the standard magic numbers, 82, 126. Here you have, I'm sure you know all the orbits in each shell by heart by now. Here's F7 halves, H9 halves, I13 halves, P3 halves, F5 halves, B a half. Okay, and what you see is that as you turn on the deformation, as the nucleus goes from spherical to something shaped like a prolate American-shaped football, each of these levels, which can contain 2J plus 1 particles, there's degeneracy breaking. So this is F7 halves. I know you can't read it back there. F7 halves can contain 8 particles. And in the independent particle model, all those particles will be at the same energy. As you turn on deformation, something happens, something changes. And you get 4 levels out of this F7 halves, and we'll see what they are. And so the energies change. And so the Nielsen diagram is just simply nothing more than the independent particle model shown for every possible deformation. Okay? If I picked the deformation at point 3 and showed these levels, that would be the equivalent of showing the independent particle model for 0 deformation. It's just convenient to show everything all at once. Okay. So we want to understand this. We're going to do it in 2 ways. A formal derivation, which I'm going to go through very quickly later on, because it's in every textbook, and there's nothing I can say that you can't see in the textbooks. But first I want to derive it without any calculation whatsoever. This is a slight lie. You have to be able to calculate a cosine, but that's all. Okay, so first of all, a comment about deformation variables. We've talked a lot in this course about beta. You just saw epsilon on that diagram. There's also a thing called delta. And by that I don't mean, well, I'll say this first. This delta, to all intents and purposes, these are about equal. They're all within 5% of each other. So for the purposes of this course and almost everything you'll ever do, you can treat them as equal. They arose for different reasons, which I won't go into unless someone really insists, but you can treat them as more or less equal. There's an older parameter which I haven't seen in years, which is called eta, and that's about 20 times beta. And I just write that there in case you ever see it. But beta, epsilon, and delta are effectively interchangeable. Okay, so for a nucleus we have 2 shape parameters, beta and gamma. We're going to ignore gamma today. And so beta is the quadrupole deformation, and you have the 3 Euler angles, which tell you the orientation of this nucleus in space. As I said, we're going to assume that the nucleus is axially symmetric. Okay, so the Nielsen model. Here's the shell model, or independent particle model. And if I pick some random deformation, I would have some levels, and that would be the Nielsen predictions for that deformation. But, as I said, it's convenient to plot all the deformations on one single diagram, and so you have these diagrams. So I show 2 of them here. One is for the shell from 50 to 82, and the other is for the shell 80 to 126. And the main thing I want you to see here is the similarity. In each shell, you have a bunch of orbits going down, some orbits going flat, their energies don't depend on deformation much, some orbits going up, and then you have some orbits from the next shell coming down, and some orbits from the previous shell coming up. You know, the same thing here, a bunch of orbits from the shell we're talking about, and then some sometimes called intruder orbits from the next shell, or extruder orbits from the lower shell. Okay? So, since these diagrams are very similar, if we can understand any one of them, we can effectively understand all of them. So I'm going to use this one mostly, almost solely. And so let's look at that again. And then I want to simplify it even further. Here's the 82 to 126 shell. We know that the 50 to 82 shell is similar in behavior, and these are just the last orbits from that shell that are rising up. They're sort of equivalent to these orbits which are rising up. These orbits from the shell above 126 that are coming down are functionally equivalent to these ones coming down. So all we have to do really is understand this group of levels. And if we can understand that group of levels, then we're in pretty good shape. So what I'm going to try to do is explain that, and I just isolate it here. So this is just a blow up of this section here. So this is what we need to understand. We need to understand why these split, and if you look carefully, you'll notice some of them curve. and we need to understand why they curve. Each of these levels, or orbits as they're usually called, has some numbers attached to them. And you saw this in Augusto's lecture yesterday, and you didn't explain these quantum numbers, right? I don't remember you explaining them.
No.
I will explain them and tell you what they are. They look complicated, but they're actually very simple. And they help you understand what the nucleons are doing. Speaking of nucleons, last night we went into town to a restaurant. We passed a restaurant called the Nucleon. Yeah? Is that good? Is it related to Ganil?
No.
No to both of them?
No.
Okay. Sort of appeal. Okay, so what do we need to understand the Nielsen diagram? We need two ingredients. What do you think they are? What about the nuclear force? How about short range? Okay. Sorry? So what we need is that the nuclear force is short range and attractive, and we need two-state mixing. Okay, these two ingredients are all we need to understand the Nielsen diagram. And when I say all we need, I mean just that statement, nothing more. We don't need to calculate anything. We just need to know this statement, and we need to know a little about two-state mixing. All right? Okay, so here's the Nielsen model. Here's a deformed nucleus. It's non-spherical, so it can rotate. The Nielsen model is a model that is solved in the body fixed frame of the nucleus. That is, it describes what happens inside this nucleus. But the nucleus exists in space, so it can also rotate. And the reason we can separate that is because, or at least approximately separate it, is because the frequencies of orbits and the frequency of rotation of the nucleus are very, very different. So even if the nucleus is rotating, during an orbit of a particle, you can treat the nucleus as approximately stationary. Okay, and so we can separate those degrees of freedom. Note one interesting thing so if the nucleus is rotating this way, and one particle is going around this way, and another is going around the opposite way, if it's rotating slowly, it doesn't matter. These two particles basically see the same thing. If the nucleus is rotating very, very rapidly, then there's a little bit of a difference between what this particle experiences and what one in the same orbit going the opposite way experiences. And that effect shows up at higher angular momentum states and is known as signature splitting. We won't discuss it, but just remember that if you're studying higher spin states, that can be an effect that you need to worry about. Okay. So I want to define a coordinate system. So here again is our nucleus. Here is the z parameter, the z-axis, the axis of symmetry. Everything is symmetric around that. And here is the orbit of a particle. So imagine I have a particle going around the nucleus in this direction. So its angular momentum, little j, points in this direction, perpendicular to the orbit. And there are two quantities associated with that angular momentum vector. One is the angle relative to this axis, theta, and the other is the projection of that angular momentum on the z-axis. Okay? And if you remember when I discussed even nuclei on last Tuesday, not yesterday, anyways, a number of Tuesdays ago, I used the quantum number k in talking about beta and gamma vibrations. If you remember, there was a thing called the gamma vibration, which had k equals 2, and a sequence of rotational levels 2, 3, 4, and so on. This is the wrong quantum number to use here, but I'll tell you why I'm going to use it. Properly speaking, the projection of the single particle angular momentum on the z-axis is called omega. Okay? And the reason is that k is the projection of the total angular momentum on the z-axis. The total angular momentum consisting of the particle angular momentum plus any rotational angular momentum. But in an axially symmetric nucleus, the rotational angular momentum is always perpendicular to the z-axis, so it has no projection on the z-axis, so k and omega are similar. And so I properly should be using omega as a quantum number, but I will use k, and I think most people probably use k. It's really carelessness, but it's become very ingrained in the way we think about things. Okay, it's also good to get away from omega sometimes because, you know, there are more concepts in physics than there are letters in the alphabet. And so very often we have to use the same letter to mean different things. And yesterday, Augusto used omega to mean the degeneracy of the shell. And here, for an odd particle going around the nucleus, it means the projection of the angular momentum. And so, okay, it can get confusing. Anyway, so I'm going to use k for that projection. Okay, and notice that sine of theta is k over j. Okay, all right. I said a few minutes ago the only thing you had to be able to calculate was cosine of theta, sine of theta, actually. Okay, so this is the coordinate system. Whoops, whoa. This is the coordinate system. Oh, there's my comment about omega. I forgot that I'd written it here. So we will use k instead of omega. Here's the coordinate system we're going to deal with. And so all we have to do is think about this and what the energies are of particles going in different orbits with different k values will be. Okay, so the question is, you have shell model energies for a spherical nucleus, and now you deform the nucleus. Let's consider two orbits called 1 and 2. I could have called them 16 and 17, or whatever, but I chose 1 and 2. Okay, so this orbit goes around the equator, and this goes what I call polar. And the key thing to notice is that the orbit 1 is closer on average to the bulk of the nucleus. The nucleus is deformed in this direction than orbit 2. And since the nuclear force is attractive in short range, that means that the particle in orbit 1 will feel a stronger attractive nuclear force than the particle in orbit 2. And therefore, its energy will be lower. Is that clear to everybody? It's pretty simple, and that's the Nielsen model right there. You've got 90% of it already. So let's just look at what these signs of theta. I want to just calculate k over sine of theta, in other words, basically k over j, for different values of k. So I'm going to take a particle in an I13 halves orbit, and an I13 halves orbit will have projection quantum numbers 1 half, 3 halves, 5 halves, 7 halves, 9 halves, 11 halves, and 13 halves. And so here's a table where I have those k values from 1 half to 13 halves, the angle theta corresponding to those k's. So that angle theta is just related to having, if the angular momentum goes this way, if k equals 13 halves, you'll have 1 theta. If it goes like this, you'll have a different theta. And then down here I have, and that's just calculated from sine of theta is k over j. And down here I have the differences between adjacent angles. And what you see is that for k equals a half, that corresponds to an angular momentum going like this. And k equals 3 halves, which is an angular momentum at a slightly larger angle, and so on. The changes in angles for low k are very small, and the changes in angle for higher k are greater. Okay, so if you take that information and go back to here, you would expect that the energies of particles in low k states would be more similar to each other than energies of particles in adjacent high k states, simply because for the high k states, the angle changes more as you go from one k to the next. Okay, clear? Okay, so let's take the I13 halves, and this is what we would predict from this argument. So this axis here is deformation. I didn't write it, but it's deformation. Here's the I13 halves single particle shell model, independent particle model orbit. And as you deform the nucleus, the orbit with k equals a half, let me go back for a second. K equals a half is an orbit where this angular momentum vector is pointing nearly vertically, so it has a small projection on the z-axis. That corresponds to a particle going in an equatorial orbit, so it's close to the nucleus. And the more deformed the nucleus is, the closer it is, and therefore The more deformed the nucleus, the lower the energy of this K equals a half orbit. Okay? For a spherical nucleus, all these energies are equal. As you deform the nucleus, the K equals a half. The equatorial orbit will go down, down, down in energy. K equals 13 halves, which is an orbit going in this direction with its angular momentum pointing this way, will go higher in energy as the nucleus deforms because the nucleus will squeeze in this direction. And so that goes up. And the spacings between these orbits will not be uniform, okay, because the change in angle of the orbit from 1/2 to 3/2 is less than the change from 9/2 to 11/2. Okay? Now, what you're seeing here, the general phenomenon is degeneracy breaking. In the independent particle model, you can put 14 particles, 2J plus 1, in this orbit. In the Nielsen model, the energies of the particles depend on this particular angle of the orbit. Okay? And you can put 2 particles in each of these orbits. The reason you can put 2 is you can have one going around the nucleus this way, and the other going around the nucleus this way. And if you make the approximation that the nucleus isn't rotating while the particle does that orbit, there's nothing that distinguishes these two. They have the same energy. As I said, if the nucleus is rotating very fast, that breaks down, but we won't take that case now. So you can put 2 particles in each of these orbits. The orbits are K equals 1/2, 3/2, 5/2, 7/2, 9/2, 11/2, 13/2. That's 7 orbits. 1, 2, 3, 4, 5, 6, 7. 7 times 2 is 14. That's the same number of particles you can put in the apparent orbit. Okay? Okay. So, imposed on a Nielsen diagram then, what you've just seen is this effect. The I13 halves orbit splits into 7 individual orbits, highlighted in red here. This orbit coming down here will have K as a half. This one K equals 3/2, 5/2. Notice these are very close together. Spacing increases a little. 7/2, 9/2, 11/2, 13/2. Okay? And most of understanding the Nielsen diagram is just applying the same idea to each of these other single particle energies, orbits. So F7/2 has projection quantum numbers K equals 1/2, 3/2, 5/2, and 7/2. And so it'll break up into 4 Nielsen orbits, as they're called. This will be the K equals 1/2, K equals 3/2, K equals 5/2, K equals 7/2. This is H9/2. It'll break up into 1/2, 3/2, 5/2, 7/2, 9/2. We've already talked about this. The P3/2 will break up into K equals 1/2 and 3/2. F5/2 into 1/2, 3/2, 5/2. The P1/2 will just have a single one. Yes?
Sorry, maybe I missed something, but is there any simple way to explain why the evolution of the one shell is sometimes linear with the deformation and sometimes not?
You mean, why do some of these curve?
No, but I mean, some curve like really have a linear trend and some other do not.
Yeah, there is a way, and that's exactly the next thing I'm getting to. In fact, I think when I click this, there's going to be some text over here which says, okay, we've got it all, but what about the curvature? Okay? Yes?
So, can we just go back to that first picture of the 2 different ways the circles can go around the nucleus and how this explains? Oh,
There?
you passed it. the way that you said, once you understand this, you have the Nielsen model. Yeah, this. Yep,
That.
right here. Yeah.
Okay.
So, from our 2-dimensional cross-section, I'm imagining this red circle is prolate,
Yes?
and in which case I can see what's happening, but what if this cross-section, I don't know, are the arguments all the exact same for oblate?
Yeah, we'll talk about that.
Okay.
Yeah. Well, they're the same but upside down.
Okay.
Okay? If you have an oblate nucleus, a disk, suppose this were, well, let's see, we have a disk. I don't want to drop that. I'll use it. Do you know what page this is?
Absolutely.
So here's an oblate nucleus blown up. Okay, and if I have a particle going around this way, okay, or this way, okay, the energy will be very different in the 2 cases, all right? And we will talk about that in a minute. So you can use exactly the same argument, okay? But clearly, the k equals 13 halves instead of the 1 half will be the lowest.
So our definition of z with the prolate and
Yeah, okay, I should be careful the way I say that, but we'll talk about that. Yes.
Okay, so you're going to talk about why do we have some linear trend of the Newton
Yeah.
kilograms and later in Kings, but I noticed, I think there is one of the D5 half, which first starts to go lower in energy and then starts going higher in energy.
Yeah, that, so
Are you going to talk about this?
I think you were thinking about this one
No, down, absolutely down.
down here?
Yes, you see, it first goes down and
Yeah.
then goes up.
Okay, that's analogous to this,
Ah, yeah.
okay? And yes, I will talk about why that happens,
Okay.
okay? And actually, you can imagine that the wave functions of these particles depend on the deformation. And just by thinking about it, you'll actually be able to deduce the wave functions, and you'll see that this wave function of this particle has different features than the ones that are straight. Okay, so these two questions are linked, and we'll come to those in a minute. Okay? All right, so this is the essence of the Nielsen model. You just repeat this idea, I've said this already, for each J orbit, and you see these patterns. Now there's one thing that's missing, as you pointed out in your question. Some of the lines are curved. What does that mean? Where does that come from? Anybody have an idea where that could come from?
Fancy calculations.
Sorry?
Fancy calculations.
No, very simple calculations. Sorry? So I'll give you a hint. There were two ingredients we needed, that the nuclear force was short range and attractive, and two-state mixing. So we've discussed what happens because the nuclear force is short range and attractive. Can anyone guess where the curvature comes from? Okay, it's two-state mixing, and we'll see that in a moment. Okay? So we need to understand this curvature. It's just an example of the curvature. Okay, so you see these lines are curved, some of them. And some are straight, by the way. Notice, before I leave this, notice that all of them start off straight. Maybe only for a little while, but they all start off straight. Okay. So, what we've talked about so far is the energies in a field of a certain shape. That's a diagonal effect. But the interaction that generates the Nielsen model also mixes the wave functions of these different single particle states. Okay, and the mixing will depend on their energy separation, which changes with deformation, and it also depends on which orbits they are. Only states of the same K can mix. Okay, now later we'll generalize that, but for this pure simple Nielsen model, only states of the same K can mix. Okay, so now remember our discussion of two-state mixing earlier in the course. And I want to look at how two states mix as a function of their energy separation. So, if you remember, if I take two states that mix, they push each other like this, okay? And if they were further, I'll call that further apart. If they're closer together, for the same interaction, they will push each other more. Okay? Remember that? Okay, so now, suppose that I take a case where the unperturbed separations change as a function of deformation. Okay, so here's the deformation axis. Here's the deformation axis, and I'm taking two spherical single particle levels whose initial linear behavior starts off so that they're approaching each other. So what's going to happen due to the mixing? Well, here, this orbit will be pushed down a little, and this will be pushed up a little when they mix. Here, it'll be a bigger effect, and here it'll be a bigger effect. And so the net effect is that they will curve. Okay? And that's what I'm trying to show here. if you have two orbits, two unperturbed, remember I always used phi's for unperturbed and psi's for perturbed. If they're approaching each other and they mix, they can never cross. Because remember, the closest two levels that mix can ever be is twice the matrix element. Remember the degenerate case? Okay, so they can never cross. And so what will happen is they will, that's called the the avoided crossing, or no crossing theorem. And so what will happen is instead, at the point where they would have crossed, they reflect and kind of bounce off each other. And go like that, all right? Now, if you remember, we had a table in the two-state mixing calculation of the mixing amplitudes as a function of the separation and the interaction. So this wave function here starts off very pure, just phi 2, and this starts off very pure phi 1. As the unperturbed energies approach each other, the wave functions will become a mixture of phi 1 and phi 2. At this point, they will be totally mixed. So the wave functions will be this total mixture. On the other side, this wave function will actually look more like that one, even though it started off here and you can draw this continuously. And this wave function will look more like that one. Okay? So these levels will approach each other and curve away, and that's the origin of the curvature in the Nielsen diagram. Okay? And at the inflection point, the separation has to be twice the interaction, and on the right, side 1, the wave function is predominantly, oh my god, oh no, I said it right. It's predominantly phi 2, and side 2 is predominantly phi 1. Is this clear? No? Yes?
So you mix wave functions, or you mix levels which only have same k. So for
You
example,
only mix the same K.
So for example, that would be D5 half or F5 half.
No. Those are the, let me go back to finding this diagram. Okay. So, K, so for a given orbit, like F7 halves, you have 4 orbits from it. K equals 1 half, 3 halves, 5 halves, and 7
Yes.
halves. From H9 halves, you have K equals 1 half, 3 halves, 5 halves, 7 halves, 9 halves. So the orbits that will mix will be K equals 1 half from this orbit, and K equals 1 half from this orbit.
Yes.
K equals 3 halves and 3 halves. K equals 5 halves and 5 halves.
And when you, in the end, what? Okay, when they mix very strongly and become like totally mixed, what would be the angular momentum of this level?
It'll be a mixture of the two J's.
And is that a good quantum number?
No. Hee. I was hoping someone would ask that. Yeah, so what happens, angular momentum's not conserved. Uh-oh.
I don't know. That sounds.
There must be another angular momentum in the system.
Mhm.
It's called rotation.
Rotation.
Yeah.
Okay.
But we'll talk about that. And it leads to some very bizarre effects. Okay? But you have to be patient for that. All right, so, well, since I have this here, you can see that, let's take this K equals 5 hash here, because it's very obvious. This is starting up this way, this is starting down. They would have crossed here. And what they do is they do that repulsion and then go off on their happy ways. Let me go to the next drawing that I was going to show. Okay, so here are a couple of, whoops. So here is the K equals 5 halves from the F7 halves orbit. Here's the K equals 5 halves from the H9 halves orbit. They're approaching each other. This is where they would have crossed, and they reflect and go like that. Okay? All right. Now you can actually estimate the wave functions. The wave function of this particle at very close to zero deformation is very close to pure F7 halves. The wave function of this particle at very small deformations is very close to H9 halves. As they go out, as the deformation increases, these two orbits will mix. Okay? And this wave function will be partly F7 halves and partly H9 halves. Other things too, but let's just talk about that. And this particle will be partly H9 halves, mostly H9 halves, and partly F7 halves. At the point of closest approach, they will be equal mixtures. After the point of closest approach, out here, this orbit, which is drawn as originating in F7 halves, actually has a wave function which is mostly H9 halves. And this one, which is drawn as if it comes from H9 halves, is actually mostly F7 halves. You can always tell what the dominant amplitude is just by extrapolating. If I put a ruler, a scale on here and just draw back a straight line, it goes back to there. And this one goes back to there, so you can always tell. So you can actually use this to estimate the wave functions in the Nielsen scheme. And here I give a couple of examples. Can you see these numbers? Yes? No?
Yes.
Who said that? Yeah, but you're up in the front. What about in the back? Can you see these numbers? Okay, way back there. Okay, good. Okay. So, let's look at a couple of orbits. This orbit has this name 5S523. I'll explain these quantum numbers in a minute. And this one has 5S512. So, those two orbits are this one and this one, okay? And here are their wave functions. Their wave functions look like this. They are a sum over the individual spherical single particle energies from the independent particle model times a coefficient Cj, which is a mixing amplitude. And these are always called the Cj coefficients. And this table shows those wave functions. This is J, so that's this little j, the J of the single particle orbit. And so 1 half, 3 halves, 5 halves, up to 11 halves. And this is the wave function of this orbit. So a particle in this orbit, 5S523, has a small amplitude for J equals 5 halves, has a bigger amplitude for 7 halves, the dominant amplitude is 9 halves, small amplitude for 11 halves. Just in case you can't read, this is 0.472 and 0.826. So it's dominantly 9 halves, and it has a large 7 halves component. That orbit is this one. So for small deformation, it would have been a dominant 7 halves component. After this avoided crossing, its wave function is dominantly H9 halves, and so you see 0.826, 0.472. So if I looked at a region of the Nielsen diagram that we haven't discussed here, you could actually go and pick off some deformation and look at where these orbits came from and whether they've had a reflection, and you can actually estimate the main components of the wave function. That's really remarkable. You can almost write down guesses of the main components of the wave function by inspection. You can't get the signs that way, at least I can't. Okay, let's look at its so-called partner orbit, 5S512, this is this one. And so for small deformation, it would be mostly H9 halves. When we come out here, this arrow says where this table is calculated. Okay, it's going to be mostly F7 halves. The next important component will be H9 halves. And you see 0.836 and 0.515. Notice these are almost the orthogonal combinations. 0.47, 0.82, 0.83, 0.51. So what you're seeing here is dominantly two-state mixing with some little wrinkles. Okay, yes?
Would you mind giving us a physical interpretation to the fact that two levels of the same K cannot cross?
Two levels that mix can never cross.
Yeah, but that's what we have seen. That's a more mathematical interpretation. I mean,
Mathematical
yeah,
interpretation.
well, from our point of view, we just did it, and we just mixed and see that they cannot never cross. But what does it mean?
I'm probably going to give too simple an answer. If you have two states that mix, they repel each other. And so as they approach closer and closer, they repel more and more. And if they repel, they can't cross. It seems too simple. By the way, this gets interesting if you talk about unbound levels. But it's still true that they repel. Is that?
Yeah.
Okay, it wasn't very mathematical. Okay. All right, let's do another one. Was there another hand up? Yes.
I wonder how they draw this diagram.
I'm
Because for different deformation points, it depends how you connect the curve. It will be close if you connect it by different way.
If you actually want to draw this diagram, What you do is a series of calculations as a function of information, and you look how the wave function of each level slowly evolves, and you can connect them very easily.
So I mean, if after the interaction,
Yeah.
the main component is changed, but if we just according to the main component, they will be cross, no.
You mean if you just did a calculation here and no other deformation, you might not be able to connect it so easily there. Is that answering your question? I don't think so. Ask it again.
I mean, in the region, the interaction.
Here?
In the interaction region. So if we, for different, with the change of information, we can connect them according to the main component. So if we do this way, once they are cross, no deflect.
Yeah, if you want to connect by the main component,
Yeah.
you would draw this like this. And you would draw this like this. But physically, two states that mix can't cross. And so we always draw them this way. Remember, this diagram is a sum of an infinite number of diagrams, each calculated for a given deformation. So the way of drawing it like this is sort of for our convenience. What you have at each given deformation is a wave function. And so this is a little bit of a pictorial way for our convenience. Okay? I want to do another one. There are these two in blue, which are, see the color coding, 7 has 503 and 7 has 514. Remember, I'll explain these numbers soon. So the 7 has 503, 7 has 514 is this orbit. So for small deformation, it's largely F7 halves, and then it has a avoided crossing with a particle in the H9 halves, K equals 7 halves. And so out here, which is where this table is for, this wave function will be dominantly H9 halves, this wave function will be dominantly F7 halves. And so if we look, here's 7 has 514, its wave function is 0.3 for j equals 7 halves, 0.9 for j equals 9 halves. That's this orbit, okay? So it's dominantly H9 halves, even though we draw this starting to make 7 halves. The partner orbit is almost exactly the orthogonal combination. So here's 0.323, 0.938, here's 0.937, 0.336. So it's almost pure two-state mixing, and any other amplitudes are 0.09, 0.128, very small. Okay? So you can actually estimate the Nielsen wave functions by hand, just simply by looking at the diagram. Yes?
So we can use this diagram, the energy and the deformation, can then go and say, okay, I have that energy and that deformation, and then I choose those lines and say, okay, so this should be the orbit. Can we use it in that sense?
I think so, if I understood your question.
Yeah, well, like we get some energy, like 6.3,
Yeah.
or 6.2, and then the deformation is like 0.5 or
Well,
something
say
between them.
0.22 or something.
So can we assign that one to said, okay, so this is the quantum number that it should have.
These are the quantum numbers of these Nielsen orbits, which I'll explain in a moment. And in fact, there it is. Oops. There we go. These are the quantum numbers we assign to the Nielsen orbits. This is what I call their parent state. In a sense, the diagram is misleading. What you just want to have are the wave functions for each orbit at each deformation. But if we do a series of calculations and trace it out and see how the wave function smoothly evolves, this is the way you would draw the lines. Okay. I want to come back to another question, which was it yours about the double curvatures? I think so. So this one, you'll notice first curves one way and then it curves the other. And what you're seeing there is, so first this level is mixing, this is the K equals a half orbit from P3 halves, and it's mixing with the F5 halves here, and so they repel each other, and so that gives you this convex behavior. And then as you go out here, this one is starting to mix with one of these others, I don't remember which one, and so it curves the other way. So you have a sequence of two-state mixings, and that gives you this sort of complicated thing. And so if you look at this orbit, which is 1/2 5-2-1, you would immediately expect that its wave function is going to be more complicated. It's not just going to be two major components, because you've got this avoided crossing and then another one here. And if you look at it, 1/2 5-2-1, it's got a wave function which is just spread out over all of these j's. 0.5, 0.35, 0.47, 0.43, 0.44, and small one there. Okay? So just by looking at the diagram, you can actually estimate the wave functions. Now let me make a comment about the phases. As I said, you can't estimate the signs, and if you look at different Nielsen model tables, diagrams, wave functions, you'll see different sign conventions. And I don't mean simply multiplying all of them by -1. You will see things where, you know, these two, which have opposite signs here, might have the same sign, and then these might have opposite signs. There are different phase conventions in the literature, and in most cases it doesn't matter too much, but if you take these Nielsen wave functions and then put them into some code, for example, that calculates transfer reaction cross sections, you have to make sure that code is using the same phase convention, so you can get in trouble. Okay. Yes?
I'm sorry if I didn't understand. How did you get the numbers in that table?
In the tape, how did I get them?
Yes.
I used a code, a Nielsen code, to calculate them, and this afternoon, in the exercises, that's the first thing you'll do. We have the code, it's on your server area, whatever you call it, and you're going to actually calculate it yourself. Okay, and then you'll change some parameters and see how the predictions change after you've predicted them by hand. Okay?
Just to have an idea, is it by doing matrices and...
Yeah, what you do is you take the Hamiltonian, which I'll show in a little while, the formal Hamiltonian, which is an oscillator plus a P2 cosine theta, Y20, and that matrix element mixes the single particle states, and then you just diagonalize. Okay? All right, everybody comfortable with this? Everybody feel they understand it? I don't think it's complicated. Yes?
Well, I still don't get when they are like crossing, like you see about 126, one of them comes really down,
Yeah, okay.
the other one go
Yeah.
up, and then they cross them.
Okay,
So
these can
which one
cross
is it?
because they have different principal quantum numbers, different oscillator shells. So they can't mix.
cannot, but no, but if we have an energy of 6.4 and that deformation, well, so we cannot just assign, okay, so it should be that one or this one. That's my question. So we cannot use Nielsen model?
Maybe you're asking if we have for certain energy, where do I, because usually we are used to filling the particles, so we have some boxes and we fill the particles, and at some point we have crossing of the boxes and we might wonder in which box should we put the particles. So
Okay.
for that energy,
We
on
will-
which level should we put the particles?
We will see very
Is this your
soon.
question?
Yeah.
We'll see very soon, and I think it'll be clear when we do it. We'll see how to do this for a specific nucleus. How to use the model, how to know what orbits the particles are in.
Was that your question?
Let's suppose that we are like on the region of 0.3 and 6.4. Yeah, some. We want to add some two particles. So occupy some single particle orbit. So how do we know that we are going into the formation to the left or to the right side on the diagram?
Okay, so that's a good question. So let me phrase the question my way and see if I'm understanding your question. So suppose we have a nucleus, let's say here, okay, where the last two particles are in this orbit. And now I go to a nucleus which has two more neutrons. Okay, how do I know whether to put those two neutrons in this orbit or maybe in some other orbit because the deformation has changed, right? Okay, we will see that. okay? You have, in order to use the diagram, you have to know the deformation. And first of all, the deformation changes slowly, but we will see how to do that, okay?
Because generally evolution should come from this 82 somehow curve
Yeah,
to
exactly.
126, yeah?
In general, if you start with a closed shell, the deformation here will be 0 as you start to fill nucleons. Think of the P factor. Deformation will come out, it'll maximize somewhere here, and at the end it'll curve back. And we'll see how to do that. Okay? So after I introduce the model, we're going to do practical calculations. Okay? Okie dokie? All right. So, think about what we've done. We've deduced, okay, you might want to put that in quotation marks, the Nielsen diagram without calculation, just thinking about the shape. And you can now do this for any shape. You can do it for an oblate shape, which is what you asked about, Basile, or you can do it for a hexadecabole shape. It looks roughly like this. Now, this is the only little, what do you call these things? That you get off the web. I pulled this shape off of PowerPoint. And so the nuclei don't come to points here. Just realize that it's supposed to be rounded. Okay? So you can actually calculate a Nielsen diagram for this. And in fact, you'll do that this afternoon. And you'll do it two ways. You'll do it by hand, just by thinking about it, and then you'll calculate it and see if you were right. Okay? What happened? Why did that disappear? Okay. All right, the quantum numbers. Those quantum numbers you saw, well, let me go back. Okay. They always have a bracket, you probably can't see this, with 3 numbers inside the bracket and a half integer number out to the left. Okay, here's what those numbers are. So those numbers are k, pi, n, nz, and lambda. Okay. Now, k you know, that's the projection of the particle on the symmetry axis. Should be called omega, but we tend to use k. Pi is just the parity. Now, let me come back. Parity is an important idea. So in the 82 to 126 shell, as you know, most of the orbits have negative parity. F7 halves, H9 halves, P3 halves, F5 halves, P a half. There's one orbit with the opposite parity, I13 halves. Okay, that's positive parity. It has a name. It's often called the UPO, unique particle orbit, and because it's the only orbit in this shell with that parity. Now, somebody asked, why are some of these orbits curved, which we've discussed, and why are some straight? So these are almost purely straight. Now you can answer that, right? Why are those orbits straight?
Because there is no same kind of parity level.
Exactly. Is that what you were going to say, whoever was over here? Okay. There's nothing else it can mix with. Now, that's not quite true. It in principle could mix with orbits from this shell, which has the same oscillator shell, but that's pretty far away, and so the mixing is very small. And you will see that this afternoon. Okay? So, okay. So, k is the k value, pi is the parity, n is the principal quantum, the oscillator shell, and going back, this is oscillator shell n equals 5. If you just count up from the bottom, you'll see that. And so the first quantum number in brackets for all of these orbits, except the I13 halves, is going to be a 5. The I13 halves comes from the next shell up. It comes down because, comes down because of the spin orbit force. So it really is from oscillator shell 6, and so that one will have a 6 here. Yes?
So you've explained how we know which K projections are going to go up and down and so on, but how do we know because these levels are crossing a lot, so it seems like the splitting in this K value is large compared to our original shell value.
Yes. Yeah.
So how do we get a grasp for why this is so large of an effect?
So the mixing depends on 2 things, as you know, the energy separation and the
Short range.
the matrix element. The energy separation, that's clear, you can see that here. The matrix element are the matrix elements of Y20 between single particle orbits, and that depends on which single particle orbits you have. Generally speaking, if you have 2 orbits differing by 2 units in orbital angular momentum, okay, they will tend to mix more. And if you have things like F7 halves, P a half, oh, that one actually will, it's so far apart, but H9 halves, P a half will not mix very much. So the quadrupole interaction will mix orbits differing in L by 2.
But even without mixing, like these I values that are completely straight, the bottom one is going to go down almost by an entire unit of energy.
Oh, you're saying the effects are big?
Yeah.
Oh, they're huge, yeah. They're huge, and you'll calculate them this afternoon. It depends on the strengths. It depends on the orbits of particles in a deformed nucleus. But yeah, they're big effects. Okay, so the second quantum number is in many ways the most important. It's NZ. So it's the number of nodes in the wave function on the z-axis, the symmetry axis. And so you can think of it this way. The larger NZ is, the more the wave function is extended in the z direction, in the direction of the axis of symmetry. Okay? And if you remember, a particle going around the nucleus, around the equator, around the axis of symmetry, is closer to the nuclear matter, its energy will be lower. So the lowest lying levels will have the highest values of n sub z. Okay. Lambda is not so important in practice except for one aspect when it comes to Coriolis mixing. It's the projection of the orbital angular momentum on the z-axis. Sigma, which I don't write up here, is the projection of the z component of the orbital angular momentum on the z-axis. And K is the sum of the projection of the orbital angular momentum and the spin angular momentum on the z-axis. So K is always lambda plus or minus a half. If you specify lambda and K, it's redundant to specify sigma, so usually it's not said. Okay, one other thing, n sub z plus lambda has to be even or odd according as n is even or odd. So how do you assign these quantum numbers to these orbits? The basic idea is that the more the particle is going in an equatorial plane, the more it's aligned with the nucleus, the larger n sub z is going to be. Okay? And there are 2 ways of doing it. Well, we'll talk about them. So the lowest orbit is most aligned with the bulk of the nucleus. It's most extended in the z direction, so it has the largest n sub z and the smallest k. Knowing that, we can assign these quantum numbers to any orbit we want. Okay, and so I'm going to do that now. I'm going to do it 2 different ways. So I blew up the 82 to 126 section, and also the 50 to 82, because the this is mostly n equals 5, right? Oscillator shell 5, F7 has, H9 has, P3 has, F5 has, P a half. But because of the spin orbit force in the shell model, the H11 halves is also a member of that oscillator shell, and it's going down to the next shell below. So if we want to assign all the quantum numbers to the n equals 5 orbits, we need to include this. Okay, so there are 2 ways of doing this. I'll do both of them. These dots just simply help you see the orbits. The fact that they're moving around in deformation means absolutely nothing. It just means I didn't have room to put them over here. It's just, okay, so that means nothing. Okay, so the lowest of all the orbits from the n equals 5 shell is going to be the k equals a half orbit, okay, from the H11 halves, because single particle energy is lower. And that will have k equals a half, so if you can't read this, it says 1 half. And then in the brackets, there are 3 quantum numbers. N equals 5, all of these will be n equals 5. N sub z is 5, it's the most extended in the z direction. And if you remember, n sub z plus lambda has to equal n, so n sub z is 5, big N is 5, so lambda must be 0. So you have 1 half 5, 5, 0. Okay? Now we go to the next orbit. That's going to be a k equals 3 halves orbit. Okay? It will be a little less extended in the z direction. The k, the orbital angular momentum is tilted a little. And so that will be 3 halves, 5, 4, 1. So I've reduced n sub z by 1, from 5 to 4. And to make n sub z plus lambda equals 5, I have lambda equals 1. Is that clear? So the next one, pretty obvious I think, will be 5 halves. So 1 half, 3 halves, 5 halves, 5, 3, 2. The only thing that's changing is the number of z quanta, because the orbit is gradually tilting with respect to the nucleus from being equatorial to polar.
Sir.
Yep.
So why this NZ plus lambda is going to be the total quantum number?
Because I don't know. I don't remember. Do you know off the top of your head? Why nz plus lambda has to equal capital N? I'll find that out. I've forgotten. Good question. Okay. Okay, so the next one is 5 has 5, 3, 2. So what will the next one be? So we've had 1 half 5, 5, 0, 3 has 5, 4, 1, 5 has, where is it? 5 has 5, 3, 2. Next one will be,
7 halves, 5, 2, 3.
he said 7 has 5, 2, 3. Does anybody agree with him? Anybody disagree? Does everybody see where he got that from?
Yes.
You need a coffee break, I think. Okay, so we started off, we're talking about the n equals 5 oscillator shell. So the first quantum number in the brackets is always going to be 5 for these orbits. The lowest energy orbit will be k equals a half. So it'll be going around the nucleus this way. And it will have the largest value of n sub z, the most extension in the z direction. And so that's going to be 1 half 5, 5, 0. As we now go with orbits that are tilted more and more and more to the z-axis, the k value will increase, 1 half, 3 halves, 5 halves, 7 halves, and so on. The n sub z value will decrease, and so you will have 1 half, 5, 5, 0, 3 has 5, 4, 1, 5 has 5, 3, 2, 7 has 5, 2, 3, as you said. What's the next one? Aha! You can't see it there.
9 of 5, 1, 4.
9 has 5, 1, 4. Very good. And the last one?
9 of 5, 0, 5. Sorry, 11 of 5, 0, 5.
11 has 5, 0, 5. Everybody see how we got that? Okay. Now let's go to the next orbit. So F7 halves. The lowest orbit is going to be k equals a half. And it's going to have the largest possible extension in the z direction, except it's higher in energy than this. This has 5, 5, 0, so this has to be 5, 4, 1. You just reduce n sub z by 1. And now you can do the others very easily. This is 5, 4, 1. 3 has 5, 3, 2. 5, where is it? No, sorry. So 1 half 5, 4, 1. 3 has 5, 3, 2. 5 has 5, 2, 3. And 7 has 5, 1, 4. Now we go to the next orbit, H9 halves. And you have 1 half 5, 3, 0. I've reduced n sub z by 1. The next orbit will be 3 has 5, 2, 1. 5 has 5, 1, 2. 7 has 5, 0, 3. And I can't go any lower, so it's going to be 9 has 5, 0, 5.
Sir,
Yes?
sir, here it is not NZ plus lambda is equal to total number of quantum number.
Yeah, I just saw that. And you know, that's a very good point. I said something completely wrong before. I said that n sub z plus lambda has to equal capital N.
Only for the high J.
Only for the high J. Okay. Okay, so do you see how this works? Is everybody totally confused, or they get it? Okay. There's another way of doing it, and at the risk of confusing you a little more, I'll say what that is. What we did here is we started with all the various orbits from a given single particle state, and we assigned their quantum numbers. And then we went to the next single particle state and assigned their quantum numbers, and then the next. What we could do alternately is take all the orbits with k equals a half. Okay? Maybe that's easier. So the lowest one is going to be 1 half 5, 5, 0. The next k equals a half will be 1 half 5, 4, 1. The next k equals a half will be 1/2 530. The next k equals a half will be 1/2 521. The next one will be 1/2 510, and the last one will be 1/2 501. So maybe that's easier. You take a given k and you just sequentially reduce n sub z. Yes?
But what about the last column number? Because sometimes it's 0 and sometimes it's 1.
Yeah, the sum of the two n sub z and lambda has to have the same parity as the principal quantum number n.
Okay.
So it's either odd or even. Okay. Is that clear?
Yes.
All right. Why don't we, well, what comes next? No, that's how do we use the model. So I know it's only 10:20, that's 10:26. Stowe and me, I think we do it both ways. I tend to go through an orbit more than I go through a k value, but it doesn't matter. Okie dokie? All right. So now, how do we use the Nielsen model? Okay, so it's similar to the independent particle model, except instead of having 2j plus 1 degeneracy, where we can put, say, 8 particles in an f7/2 orbit, we now can put 2 particles in each orbit with a given k value. So instead of having 2j plus 1 degeneracy, we have 2-fold degeneracy. As several of you have asked already, in order to use the Nielsen model, we need to know the deformation. How do you know the deformation? Well, actually, you already know the answer to that question, but we'll discuss it anyway. So you need to know deformation. And then, the Nielsen model is a model that applies to the nucleus, so it's in the nuclear frame of reference. But these nuclei live in the lab, and they can do things in the lab that we have to add on, namely rotation. Okay, so we have to somehow get the deformation, fill up particles 2 by 2, and then add rotation. Now the filling up particles 2 by 2 is very simple. It takes advantage of something you've heard many times during these weeks. So what you do is you take the Nielsen diagram for whatever kind of particle is the odd one. You assume that all except the last odd nucleon are coupled in pairs to 0. You know that pairs of particles like to couple to angular momentum 0. You've heard that from almost all of us at one point or another. And so you just mentally place 2 nucleons of whatever the odd type is into each Nielsen orbit, starting from the bottom. You fill up to where the last odd nucleon would go, and the orbit that that last odd nucleon goes into tells you the ground state of the nucleus. Okay, we'll do this so you'll see it. Okay, and then excited states just can be obtained by taking that particle in that last odd orbit and changing its orbit. Just like we did in the independent particle model, where you could have, say, something filled up to the d5/2 orbit in the 50 to 82 shell, and you can put it up into the g7/2, so on. Okay, and then for each of these states, a state meaning all the nucleons assigned to orbits in the Nielsen model, and the last one defining the state, you add a rotational band. That's all that's involved. So the model is extremely simple. Somebody asked about seniority. It's sort of a seniority in one model where you couple everything to 0 and don't worry about anything else except the last particle. Now you know from talking about residual interactions in the independent particle model that, say, if you take a nucleus like lead-210, those last 2 particles couple to 0 and you have a 0 plus ground state, and then you can make a 2 plus state at some energy, 1.3 MeV or something like that. In principle, you could do that and add that into the Nielsen model. Essentially, nobody ever does it because by the time you get up to 1.5 MeV, it's usually complicated enough that you're not actually using the model. Okay, so we have to know the deformation. You already know the answer to this because we've discussed it. You can get it in 2 ways. If you remember, I talked on one of the first 2 days about Be2 values in the neighboring even nucleus from the first 2 plus state to the ground state. That matrix element, oh, this should be squared, is proportional to Q squared, which is in first order proportional to beta squared. So from those Be2 values, you can get the deformation. And I meant to put this slide in, but I forgot. forgot, so I'll just draw it. If you remember, there was a plot of BE2 values, of betas that were obtained from, this is a function of mass, say in the rare earth region. These betas were obtained from the BE2 values, and in the middle of the rare earth region, you kind of had a region of saturated deformation about 0.3 or so. Remember that plot? I'm sure all of you remember all 712 slides that have been presented so far, but I hope you remember this. Okay, so that's one way. So you just look at the BE2 value in the neighboring even nucleus, and you can extract beta. Okay? You can also get it from the rotational energies in the neighboring even nucleus. You know that the energy of the 2 plus state is given by h bar squared over 2I times j plus 1 minus j of the ground state. That's 0 for an even nucleus. So j, for the 2 plus, j is 2, so that's 2 times 3 is 6. So the 2 plus energy is 6, h bar squared over 2I. So if you simply take the neighboring even nucleus, one sec, the neighboring even nucleus, divide that energy by 6, you can get the moment of inertia, and then you use this formula, for this first order formula to get beta. Okay? Yes?
Can I come back for a while to the seniority? Is it really a point to talk about it? Because like if we because
I
in
agree
the
with you.
Nielsen model we break the symmetry like this
Yeah,
SU2, yeah. So we cannot we break all the chains of the symmetries.
I agree with you. I just meant it in the sense that we only take one particle, and we don't worry about all the
You
other.
said something like a seniority number. You didn't say that it's a seniority number.
Okay, well that's, I hope I said something like that. I mean, I didn't mean it in a rigorous way. I meant that we just pair all the even numbers of particles to the angular momentum 0.
So generally, if we are going into Nielsen model, we pay the price for breaking all quantum numbers like this seniority and so on, yeah?
I guess I would say yes. Is that right?
Say again?
In the Nielsen model, you break all quantum numbers like seniority, and I haven't thought about it that way. Probably.
But Nielsen model originates somehow from the shell model.
Sure, it's just a shell model for a
And
different
in
shape.
shell model, do we really need to consider seniority?
Well, that's why I'm not answering really. Let me make one other comment. Another way to see it is if you put two particles in an orbit with k, with a particle going one way and going the other, that's angular momentum 0. Okay, so there are two ways of getting the deformation, either from transition rates or the energy spacings. In practice, there's a third way. You know approximately the deformation anyway because of this diagram, and you look on the Nielsen model. You can also do it that way. Look on the Nielsen model and see which deformation works the best. Remember, a basic fundamental point. These are collective models, not the right word. These are phenomenological models. And they can tell you what the nucleus is doing. They cannot tell you why. You need a more fundamental microscopic theory to tell you why a nucleus has a certain deformation. So whatever technique we can use to get the deformation is fine. Okay, so we're going to do an example. We're going to do 171 YB, which has 70 protons, 101 neutrons. The very first day I asked you to do an independent particle model estimate for 169 YB. And what I wanted you to see was that the independent particle model completely failed. So I hope you all remember having failed miserably with that exercise. And I meant to show you 169, but for some reason my brain jumped. And I'm going to show you 171, but it doesn't matter. Okay, so here's the level scheme for 171 YB. These are the low-lying levels. 1 minus, 3s minus, 5s minus, 7s plus, 5s minus, 9s plus, and so on. Here's the shell model for this region. So we have 70 protons, so we're not going to worry about those. Okay? Imagine we're going to do an independent particle model analysis. We have 100 neutrons, we're not going to worry about those. We're just going to look at the orbits of the 101st neutron. So here we have 82. There's F7 halves. We can put 8 in there. That gets 90. We can put 10 in H9 halves. That gets to 100. So the last odd particle should go in this I13 halves orbit. So we should have a 13 halves plus ground state. And we can have excited states like 3 has minus by putting the particle up there, or 9 has minus by pulling a particle out of there and putting it in there. So we'd expect low-lying states like 13 has plus, 3 has minus, 9 has minus. Well, I can't see them here. So not only don't we get the order, we don't even get the states. So the spherical independent particle model fails completely, and now we'll see how we can do this with the Nielsen model. Okay, so I've already said this. We ignore all the particles that can be paired off, and we just look at the 101st neutron. What orbit is it in? Now, the way to do this is to start from the basement and put 2 particles in each Nielsen orbit coming up to here and getting to 101. And that's fine. There are 2 problems with that. You'll never find the entire diagram on one piece of paper. And if you try to do it, you'll miscount somewhere. And so it's easier just to start from any place where you know the answer. So you know that up to here there are 82. And then just, let's say the deformation is about 0.25. And just move into here counting how many particles you have. Okay? It doesn't matter which way you go. You can take any route as long as you get to the right deformation. Yes?
Why do you say epsilon equals 0.25?
Well, we know from this diagram, and we know from the energy spacings and the even nuclei, the typical deformations are around 0.3. And so I said 0.25. Okay? Epsilon and delta and beta are a little bit different, but okay. I'm also partly motivated by the fact that this afternoon you're going to do calculations for 0.22. That's a little heavier nucleus, but in that region. Okay, so let's do it now. We want the 101st neutron. So here we have 82. If we put 2 in this orbit, that's 84. Put 2 in this orbit, that's 86, 88, 90, 92, 94, 96, 98, 100, 101. So that says, in case you can't read it, 1/2-521. So we would predict that the ground state of 171 YB is a 1/2 minus state.
Can you do that again?
Sure. I was thinking of a slide I have on density functional theory, where I say, here's my understanding of density functional theory. The slide is blank. And I click and says, do you want to see it again? So anyway, I'll do it again. So here we have 82 neutrons. If we put 2 neutrons, extra neutrons in the nucleus, we will fill this orbit. So we put 2 in each. That's 84 there. Imagine the number 84. If we put 2 more, we get to 86. Put 2 more, we get to 88. 2 more, 90, 92, 94.
But why are you moving on the diagonal?
I can move any way you want. I'll go up this way. 84, 86, 88, 90, 92, 94, 96, 98, 100.
No, but you shouldn't go.
You can go any way. All you're doing is just counting how many nucleons you need at this deformation to get 101. I can start from the bottom. 2, 4, 6, 8, 10, 12, and so on.
Yeah.
You can follow any route you want. Sorry?
He's wondering
Why? Because I can see it easily.
Okay.
I can go this way. I can do 82, and then I empty this, that's 80. Then I fill that 82, 84, 86,
No,
88.
but you.
And I can go over here, and I can come around, and I can go there, and I can wind up there. And I won't get 101 because I'll do it wrong.
No. So you have your nuclei with a fixed deformation.
Yes.
So you're wondering, for that deformation, if I start filling these shells, where would I end up?
Well, you want to find out where you put the 101st particle. So you start down at the bottom, see the cursor or the pointer down, and you just add 2 until you get to here.
No. The problem is these orbitals cross, and when you go on the other way, it might appear that.
No, it doesn't matter. You just work it out yourself, and you'll see it doesn't matter what path you follow to there. Because if you go this way, you're emptying an orbit, so you reduce by 2. You add 2, you reduce 2, reduce 2, reduce 2, add 2, add 2. I can go any way I want to there, and you'll get 101. Just try a couple of paths.
Okay.
Try your favorite path.
I think the point is for example, let's take 0.2, exactly 0.2, and fill up the pairways, and then we will end up with the point of the crossing of the 2 single particle orbits.
You mean like there?
Yeah.
Yeah.
this diagram is not that perfect, and you might have to look and see what the nucleus is telling you. Okay, I mean, if you happen to get to that point, you'll probably see two low-lying states, one corresponding to one and the other corresponding to the other. Okay? Okay, so we would predict that the ground state would be 1/2 minus, namely this orbit, and then we can make excited states. The lowest excited state would be to take one particle out of this orbit, which you can't read it, but it's 7s633, and put that particle into this 1/2 orbit. That would pair off to 0, leaving an odd particle there. So we predict a low-lying 7s plus state. We could also take this particle here and put it up into this orbit, which is 5s 512, so we expect a 5s minus state. So the lowest couple of states we expect would be a 1/2 521 ground state, there, and then other low-lying orbits, 7s 633, 5s 512, 7s 514, I didn't mention that, that's this one. So that's what we would expect. And now for each time we put a particle in one of these orbits, we let the nucleus rotate. And we get a rotational band. So let's see if we can understand the nucleus. Now I have to apologize for what's going to happen here. It's going to be in my handwriting. So you just have to live with that. Okay. You see the problem? Okay, so what I've done is notice the ground state is 1/2 minus. So think about this. In about 30 seconds, not counting weird paths to that orbit that Vasile might take, but in about 30 seconds, we predicted the ground state spin in parity of a nucleus with 171 particles. Not too shabby. Okay, so 1/2. Now you build a rotational band on that. So the nucleus has 1/2, 3 halves, 5 halves, 7 halves, 1/2, 3 halves, 5 halves, and this one is 7 halves, 9 halves, 11 halves.
But there's so much you've hidden away, right? Like,
No.
what about what the exact form of these potentials are that determines the strength of these splittings? And there's more to creating this chart than just, freehand drawing it.
Okay, and that's what you're going to do this afternoon. So the Nielsen-Hamiltonian has a couple of parameters. And so you're absolutely right. How do you know what those parameters are? Those parameters are essentially the parameters of the independent particle model. Those parameters are chosen to give you the right spherical single particle energies. And then everything else is fixed. You just change the deformation, and there's nothing else hidden. So you have to start off with a Hamiltonian that gives you those single particle energies. You'll see at the end of the lecture today what that Hamiltonian is. Okay? So there's nothing hidden. Okay, now we said that the low-lying state, probably the lowest, would have spin in parity 7s plus, 7s 633. So what's the first state we have in the sign? Woo! 7s plus. So we build a rotational band on that. 7s plus, there's a 9s plus, there's an 11s plus. Somewhere up there there'll be a 13s plus. Okay, let me go back. We also said there should be a 5s minus Nielsen orbit and a 7s minus. Here's a 5s minus. See, the first state we have in a sign, we have 1 minus, 3 minus, 1/2 minus, 3s minus, 5s minus, 7s minus, 9s minus, the 7s plus, 9s plus, 11s plus. The first state we have in a sign is this 5s minus. And so that we would assign, hope that we're right, that that's the 5s minus 512. And then the next state we have in a sign is 7s minus, and then 9s minus, and I'm not sure what this 1/2 minus is lurking there. And up here, there's a 7s minus, which is this 7s minus 514. So doing this, you can, in just a couple of minutes, understand the detailed single particle structure of the low-lying levels of this nucleus. Okay, now it's not going to be perfect. There's no guarantee, in fact, that the deformation stays rigidly constant as you put particles in different orbits, because the deformation is going to be determined by minimizing the energy of all these particles. And if you put a particle in a downsloping orbit, it's going to shift the deformation a little out that way. If you put it in an upsloping orbit, It's going to shift it this way. So there can be small differences, but this is the basic idea. And it works remarkably well. Okay? Got it? Yes.
So, yeah, in the rotational band which is built on half.
Yeah, I know what you're going to ask. Go ahead, ask it. It's a good question.
No, it's how you ascend this 5/2 states in this level, just about this 3/2 level, because it should be have more gap between this four.
You mean these energies look a little
Yeah,
strange?
right.
Yeah, they do. Anybody know why these levels? So these levels look like a normal rotational band where the spin increases, the spacing increases with spin. Anybody have an idea why this looks funny? One word, starts with a C. Next letter's O, R,
Relations.
I, O, L. Only got 2 letters to go.
Correlation,
Coriolis. We'll talk about it. So that's a good question. This band looks very strange, right? Okay, we'll talk about that. Oh, so this is an important point. I just want you to appreciate how incredibly simple this is and how it basically works. What about these predictions of the rotational energies? All that's doing is adding in this J times J minus 1 minus J0 plus 1 for the first state of the band. And these are some examples. This is an example from gadolinium-157, rhenium-183, uranium-235, and erbium-167. And these are the experimental levels. The dots are the predictions from the rotational formula. And so it works very, very well. You'll notice there's something covered up, which you'll see later, and that comes back to your question. Okay, so it's very easy, generally speaking, to predict the low-lying levels of an odd-mass deformed nucleus with a Nielsen model almost trivially. Okay, and so I could have shown gadolinium-157. That has 14 valence protons, 64, has 11 valence neutrons, 82, has hundreds of trillions of shell model or shell model configurations. And in the Nielsen, it's trivial. And why? This is another example of a paradigm shift that I talked about at the beginning. You shift, first of all, in the independent particle model, we shift from a perspective starting at the bottom to one starting from closed shells. We look at valence nucleons. Here we've shifted even further from the closed shell to the Fermi surface, and we only look at what the very last particle is doing. And all the complexity is just absorbed into the ground state. Everything else is relative to that. And these excitations are just one particle excitations, or if you think in terms of what Augusto said yesterday, they're one quasi-particle excitations. Okay, here's another example. Erbium-167 has 68 protons and 99 neutrons. Now you can all do this. Does anyone want to guess what the ground state should be? Well, actually we see it here, so that's not hard. So let's do 99 neutrons. 82, 84, 86, 88, 90, 92, 94, 96, 98, 99. I purposely took a Vasilian path. Sorry, but it was a good question. So I predict that the last particle should be in the 7has plus 633 orbit, ground state 7has plus. Now if you look at nuclear data sheets, you'll often see these orbits listed. Be careful, there's some mistakes. So this should have rotational states 7has plus, 9has plus, 11has plus, 13has plus, 15has plus, 17has plus, 19has plus. Notice they line them up nicely for you. Okay, what's the first other state we could do? Well, we could take a particle out of this 7has 63 and put it in 1.521. This has 99 neutrons. Remember, 101 was there. So we can make the 1.521 orbit. You get 1 half, 3 halves, 5 halves, 7 halves, 9 halves, whatever, I lose it. What's the next state that's not accounted for? All these are accounted for. There's a 5has minus. 5has minus state, and that corresponds to, taking a particle from here and putting it into the 5has 512 orbit. Then you get 5 halves, 7 halves, 9 halves, and so on. And you can do the rest. Okay, and so in the end, you can account for essentially all of these levels. You see these Nielsen labels all the way up there in seconds. Okay? And then having identified the Nielsen orbits leads to other predictions. For example, you can predict single particle transfer reaction cross sections like DP or PD. Okay. Here's another example. I can go pretty quickly, I think now you get the idea. For your homework, you're going to, not homework, for your exercises, you're going to do the example of tungsten 183. Here's hafnium-175, has 72 protons. 175 minus 72 is 103. And so I think by now you know it's going to be, here's 101, that's going to be 5s512. There it is, 5s, 7s, 9s, 11s, so on. And then you can make an excited state by taking a particle out of this orbit and putting it into here, leaving the odd particle in that orbit. And then you get 1 half, 3 halves, 5 halves, 7 halves, and so on. You can also take a particle out of this orbit and put it into this, and you get 7 halves plus 6, 3, 3, 9 halves plus 11 halves plus 13 halves plus 15, and so on.
So if you don't have the real nuclei spectrum and you're just looking at the Nielsen model trying to predict, so let's say I know I guess my first state is going to be this 5 halves state, and then I know there's going to be a rotational band.
Right.
But do I know, then I know, oh, this 1 half state is close, but do I know where the 1 halves is going to enter? Like,
Yes, yes.
I know it's going to be after the 7 halves.
Okay, so what do you mean by after?
So-
You mean after the 7 halves of this band?
Yeah, like how do I know?
Okay, so you know that in the following way. You predict the energies by starting off with a particle in a given orbit. You apply the rotational formula, h bar squared over 2I times jj plus 1, minus jj plus 1 of the ground state of that orbit. And you know h bar squared over 2I from the neighboring even nucleus. Deformations don't change that fast. So you can then predict the exact energy of the 7 halves, the 9 halves, the 11 halves. Here, the excitation energy, let's say we're at this deformation, the excitation energy of the 1 half 521 is given by this distance, which you can read off on the scale here, which is cut off here. And those scales, let's see. Those scales, this is not the actual units. You have to multiply this by a factor, but I'll talk to you about that later. It's roughly 7. You have to multiply. Okay, so does that answer your question?
Yeah.
So you just go yeah, you just go marching up, you apply the rotational formula for the rotational states, and then read the energies off here, and okay, I mean, it's a simple model, it's not gonna work exactly. And there is an effect due to pairing, which I'm not gonna go into, which tends to make the energies of the orbits near the Fermi surface closer to 0 than you would have expected just by reading off this drawing. Okay, maybe we can talk about that if we have time. But don't worry about that, it's a small effect.
So let's assume that you don't know the deformation of the nucleus, and you start feeling the orbitals. So how do you do it?
All right, so I would say, well, first of all, if you know the deformation of a neighboring nucleus, you could probably start off using that and see if it works. But I would think it would be very unlikely, experimentally, to have a detailed set of levels for an odd mass nucleus like this and not know the energy of the first 2 plus of a neighboring even. That's very unlikely. So in practice, it's not really an issue. Now, if you're in a region of very rapid shape change, that can be an issue, but then the model probably isn't going to work so well anyway. Okay? So, you know, you're not going to have a level scheme like this and know nothing about the neighboring even nucleus. Okay? Okay, here's 179 happening. I don't think I need to go through this, honey. It's pretty trivial, right? Okay. Okay, I want to just briefly discuss a more formal derivation of the Nielsen diagram.
Can I ask a question just about feeling the orbitals?
About the what?
About this feeling for, so now you're doing it just for ultimate nuclei. If you do it for all nuclei, would that work? I mean, you end up somewhere for the proton somewhere.
All right, let me
and
ask
then you couple them.
Let me ask a general question. Is anybody looking at odd nuclei for their theses? All right, I won't make my general philosophical comment about odd nuclei. They are extremely difficult. You can take the odd proton and the odd neutron and couple their angular momenta, and now if you have a k value for the neutron and a k value for the proton, they can add this way or this way, and so one of them will be lower and higher, and there's some rules called Gallagher-Muskowski rules that tell you which way it should go. And
So pretty complicated business.
well, it's doable and people have done it, but odd nuclei are very tough. So those of you who are doing odd nuclei for your theses, have fun. Sorry. I've studied odd nuclei. That's why I study even. Okay, sorry. No.
Maybe I should study even
Okay. Okay, so this I'm going to be very brief on because it's in every textbook. Well, not textbooks on climate change, but I mean every physics textbook. So here's the Hamiltonian. You have a potential, which is the spherical independent particle model potential, and then we add in something that induces a quadrupole shape. And this is normally written, well, actually, what have I done here? This is the spherical part. So it's a kinetic energy plus a harmonic oscillator. And normally we use a Wood-Saxon potential here. Another way of simulating that is to add a term in L squared, because that flattens out the bottom of the potential. And then there's the spin orbit term. Okay? And what happens when you add in this residual interaction is the motion in the xy direction and in the z direction are no longer the same. And so you have a different frequency in the xy direction, different frequency in the z direction. We're going to assume axial symmetry so we can combine x and y. So this is the first form of a Nielsen-Hamiltonian. What I want to do is look at it in two limits, the large deformation and the small deformation limit. Small deformation limit is usually more interesting. I'm just going to show you these formulas. So you can derive them pretty easily by assuming constant volume as you deform the nucleus. But I can write this frequencies in the x and y directions in terms of some omega 0 and something involving delta. Delta here is, remember I commented on these three different variables, beta, epsilon, and delta. In this way of doing the Nielsen model, people have used delta in the past. Just in your mind, substitute epsilon or beta for delta. They're all basically the same. And so you have a constant volume condition, which I used to know how to derive. And if you rewrite A is this equation, in terms of delta, using these definitions, you get that the Hamiltonian is p squared over 2m, a spherical oscillator, and then a term of the spin orbit and L squared terms, and then a term that involves delta and it involves y20, spherical harmonic. Okay? So this is an isotropic oscillator with L dot S and L squared terms, plus a delta R y20 perturbation. Okay? I think we can ignore this for the moment. It comes in later. I probably should have said it here. I hope. Yeah, it does. Okay. So this y20 term splits the single particle energies, or the shell model energies I wrote there. And this is the result. This is what we're talking about. We're talking about minus 4/3 square root of pi over 5. This stuff, delta and a matrix element between two different orbits of r squared y20. These, we can separate radial and angular parts. And here's the bottom line result. And this is what I want to get to. So the shift in energies on a given orbit are minus 2/3 h bar omega 0, n plus 2/3, that's the oscillator quantum. So that tells you that the shift in energy is larger the higher the oscillator quantum number. So for the high oscillator numbers, these orbits can go way sharply up and down. Delta, and then a quantity which is the most important, 3k squared minus jj plus 1, and then that's the one that depends on k. And then you have 3/4 minus jj plus 1, 2j plus 1, j plus 1, 2j plus 3. So, let's look at the structure of this solution. And you can see detailed derivations of this anywhere. First of all, it's a proportionality to the deformation, delta. Secondly, the shifts in energy, that's the changes in energy in the Nielsen model, depend on k squared. And the lowest k is the lowest for positive delta. And they depend linearly on the oscillator quantum number. Now, take a look at this quantity, but let's just take a look at this quantity. So 3k squared minus jj plus 1. So that quantity is negative. No, I'm sorry, I want to go back for a second. There are a lot of signs in here that you have to think about. There's a minus sign here. So minus means the energy is going to go down. There's a minus sign there. This quantity is negative for any j greater than 3 halves. So for most of the j's, that's going to be negative. So we got a minus sign, another minus sign, that's a plus sign. So everything here, with the exception of this, is positive. If delta is positive. We're talking about prolate shapes. Okay? So the whole expression is negative if k is less than jj plus square root of jj plus 1 over 3. All I've done is taken that 3 and taken the square root. So if k is less than jj plus 1 over 3 square root, then you'll have an overall negative sign. Okay, now, jj plus 1 over 3, square root of jj plus 1 over 3 is approximately j, okay, fairly large j. Square root of 3 is like 1.8, and 1 over 1.8 is about 0.65. So that says that this is negative for k values less than 2/3 of j. That means slightly more than half of the orbits will be going down. Okay, so for j equals 13 halves, for example, this quantity will be negative for j equals 1/2 k, for k equals 1/2, 3 halves, 5 halves, 7 halves, and positive for 9 halves, 11 halves, 13 halves. Okay?
And do we see the same phenomena you explained earlier with the smaller j value splitting less, or the smaller k value splitting less?
Yeah, absolutely. I mean, if you plug in numbers here, you'll see that. And we actually will plug them in. So this just illustrates for I13 halves, we said that downsloping orbits should be 1/2 through 7 halves, and less downsloping as k increases, and the upsloping ones, those. So here we have 1/2, 3 halves, 5 halves, 7 halves going down, 9 halves, 11 halves, and 13 halves going up. Okay. So about 2/3 of the orbits go down. What happened? Oh, okay. Okay, I just forgot what I was doing next. Okay. So I want to look at the large deformation limit. In the large deformation limit, these terms, this term is huge. These terms are negligible, so we can forget them. And then you just have an oscillator quantum situation, and the energies are simply given by h bar omega x, n times n minus z plus 1, plus h bar omega z and z plus 1/2. That's just solving the harmonic oscillator for x, y, and z. Okay? You'll still have that the energies will be proportional to delta. Okay? But now the energies will separate according to the distribution of the motion in the x, y directions compared to the z directions. Okay? And it will be, it will not depend so much on k, but it will depend on x, y, and z. And you'll see what that looks like here. So for large deformation, instead of having this kind of splitting that we've talked about, what you have are parallel sets of orbits, okay, which have the same x, y, and z quantum numbers, but they're actually going to have different k's, like this one. Let me pick this. This says k equals 5 halves, and this says k equals 7 halves, and they go out parallel forever, and you get these parallel sequences of orbits. So that's the large deformation limit. It's seldom of relevance to the low-lying states of normal nuclei, but it can come in if you have states with high deformation. Okay. I want to come to a question that one of you asked, or a couple of you actually asked early on. Namely, we always talk about prolate nuclei, but why not oblate nuclei? And this has been discussed for decades. There are many answers. I have my own explanation. There is no reason whatsoever that you should think mine is any better than anybody else's. And if I asked Augusto or Marek or Pete, they'd probably have different answers. And so I'm going to give you my answer, and you can like it or not like it. Take it or leave it. See if I care. Okay. Here is this energy expression. Okay? Let's analyze this a little. So this is negative for all except the smallest j's. And so we're left with a negative sign here, a negative sign here, that makes a positive sign, times delta, this stuff here is just constant, times 3k squared minus jj plus 1. Okay? Now let's look at this expression. Okay, so for delta positive, the lowest orbits are low k, right? We saw that. And so the energy goes as minus j squared because low k is, this low k, sorry, this will be small, and this goes as j squared. So the energies will go as minus j squared. For high k, for oblate deformations, the lowest orbits will be high k. And we haven't discussed that, but let me just try to motivate that. I mean, there's no reason why shouldn't be obvious to you by now, but here we have the Nielsen diagram, and for some single particle state, I have orbits going off like this, where this is k equals a half, 1 half, 3 halves, 5 halves. Let's say this is 7 halves. What happens on the oblate side? So this is beta greater than 0, beta greater than 0 prolate. Now you can see why I don't write on the board. And this is beta less than 0 oblate. And all the arguments that led to the lowest orbit being k equals a half will now lead to the lowest orbit being k equals 7 halves. Okay, so on the oblate side, the lowest orbits will be the highest k. And now if you look at this function, the highest k the highest k for a given orbit j is obviously j. So this is basically 3j squared minus j squared. So the energies go as minus 2j squared. Is that clear? I mean, it's an approximation, but roughly. So on the prolate side, the lowest orbits, the energy dependence is basically minus j squared. On the oblate side, it's minus 2j squared. Minus 2j squared is more negative than minus j squared. And so, for example, if you plug in numbers here for j equals 13 halves, on the prolate side, the k equals a half orbit is lowest, and this thing gives you minus 48. The oblate side, the lowest orbit is k equals 13 halves, it gives you minus 78. So oblate is lowest energy, lower in energy. So nuclei should be, and it's always the case, whatever j you put in. So most nuclei should be oblate. According to this formula, they should be oblate. In some sense, that even makes sense. If you imagine a spherical nucleus, you may have a sphere. Okay, imagine a spherical nucleus, and I have a particle going in an orbit. That, if anything, makes it disc-like, so it tends to make it oblate. So according to this, you would expect the nuclei to be oblate, but yet they're not. So what's going on? Okay, here's what I think is going on. So look carefully. On the prolate side, all of these orbits have a k equals a half. All these single particle states have a k equals a half orbit. So there are many k equals a half orbits. And they mix. Okay, the wave functions mix. And so the lowest one gets pushed down. The lower ones get pushed down. They all have this negative curvature. On the prolate side, where I don't have a drawing, the lowest orbit is going to be the highest j, and there's only one orbit with that k. So it doesn't mix. So it goes down straight. And I think it's, in my interpretation, it's this curvature, which comes from the two-state mixing, which favors the prolate deformation. So mixing of low K orbits on the prolate side pushes the lowest orbits lower, curves them downward. This overcomes the inherent oblate bias that you would normally expect. Doesn't happen on the oblate side. There's only one K equals 13 halves, orbits 2 11 halves, and so on. That's my interpretation of why nuclei are prolate rather than oblate, and I don't dare look at Pete to see what his face looks like at this point. So, Pete probably disagrees, do you?
So the argument doesn't change if you, because you see, if you look at 82 to 126, the high J is spherical, the spherical point, right? You start with high J orbits and then you go to lower J orbits.
You always have the high J orbits at the bottom.
Yes.
So-
Your argument would still hold if you put the lower
Oh,
J.
okay, so that's a very good point. What Pete is saying, if I can interpret Pete, is that it depends on the fact that I had the high J orbits at the bottom of the shell and the low J orbits at the top.
The spherical.
Right, in the spherical situation. So what would happen if the independent particle model had the low J orbits at the bottom and the high J orbits at the top?
Yes, that's my question.
So my answer is that certainly would play a role, but that would be the least of the changes. I mean, the whole world would be different.
But I guess your argument would still hold, right?
I have to think about it. I haven't thought about it, but probably. But I don't know. I have to look at it.
I agree with the mixing.
But
Mixing is essentially.
But I mean, if the independent particle model were upside down within a shell, there'd be far more things that would be different. You would probably not even be sitting there. Right? Or you would look on late. Okay, so that's my argument.
Sir,
Yes.
and so there is in these two regions, one is prolate and one is oblate case, the two phenomena is different because in oblate case the energy is going down as -2 J square what I have shown, right?
Yeah.
And in the prolate state it is going -J square. And approximately, yes. And then prolate state there is another phenomenon what you told that there is many half K is equal to half.
There are many low K
Yeah.
orbits
So
and they mix
these-
and they.
Yeah, if these two is competing, then there should be a 50-50 distribution or kind of things.
Well, it depends on the strength of the mixing.
Right.
And my interpretation is that the strength of the mixing is sufficient that the prolate side wins. Yes?
What are the numbers? Like what percent, what's the prolate to oblate ratio?
Oh, good question. So let's do it up in this diagram. So these nuclei here are spherical, right? I now start filling up the shell and you begin to get deformation. You get deformation when you have enough protons and neutrons when P is 5, if you want. And then you get prolate deformations in here, pretty much constant at some value around there. And then when you get toward the end of the shell, notice you're putting particles now in upsloping orbits. If you put particles in upsloping orbits and you add up all the energies, that's going to drive the nucleus back towards less prolate deformation. And just up here at the very end, you typically get a few oblate nuclei. Okay? And part of the reason is that you get oblate driving effects once you start occupying the upsloping orbits, but those are oblate driving effects on an already prolate shape. So you first got to erase that prolate shape and then go to the oblate. And so, for example, in the rare earth region, so the rare earth region goes from tin to lead. And the only oblate nuclei are a couple of very, very heavy platinum and, well, mercury for sure, probably some platinum isotopes at the very, right up near lead. So I would say 95% of deformed nuclei are prolate. And the ones that are oblate often tend to be axially asymmetric as well. Yeah?
Why can't you evaluate how much the mixing is to see if you're correct with that?
I'm sorry?
Why can't you actually evaluate how much this?
Oh, you can. I just haven't done it. Because I didn't dare. You know, I could be wrong. No, I just haven't done it. But yeah, you're absolutely right. I mean, all you have to do is just take a given deformation, add up all these energies up to the last filled orbit, and do the same on the oblate side, and see which energy is lower.
Can you start from the Nilsson Hamiltonian and just take the P2 and evaluate that?
Yeah, you can do that too. Exactly. Yeah, because you're just looking at the differences. Okay. Now I want to talk about Coriolis effects. These are very important in nuclei. They're also important on the Earth. You all know what the yes?
Can I come back for a while? How do you, maybe that's a stupid question, but how do you know that the nuclei is prolate or oblate?
Oh, that's not so easy. The best way is to measure a quadrupole moment. And the sign of the quadrupole moment is related to the deformation.
Because isn't that you can just rotate your prolate nuclei in order to get the oblate?
No. Think about, let's start with a sphere. If I want to make a prolate nucleus, I actually said this in the first lecture, if I want to make a prolate nucleus, I stretch it in one direction and squeeze it in two. If I make an oblate nucleus, I squeeze it in one direction and stretch it in two. So I can't just rotate one into the other. Okay, so they're different, they're fundamentally different shapes. And the way to do it experimentally is to measure a quadrupole moment. You can measure that in a number of ways. The most straightforward is probably Coulomb excitation. I can't remember, are you experimentalist or theorist?
Theorist.
Well, okay, there's a technique called Coulomb excitation, which you should know about because it's a very useful one. And that way, it's difficult experimentally, but you can get the sign and magnitude of the quadrupole deformation. There are other ways. What would be your favorite way to find out if a nucleus is prolate or oblate?
I think
Coulex. So that's the official way.
But I think also, did you also show the fact that the spectroscopy is very important because the level ordering is different. So if you have a band and the Coriolis effect, as you will explain, we have different effects on low orbits.
All right, so yeah, that's a good point. That's turning the question around on you. If you assume it's prolate or you assume it's oblate and try to interpret the experimental levels with the Nielsen model, one way will totally fail and the other way will succeed. If I had tried to interpret 171 terbium by looking at the diagram on the oblate side, I couldn't possibly have reproduced the results.
Yeah, because different orbits are available.
Because the orbits are different energies, and so that's another way. It's not a measurement, but that's evidence. Okay? All right. Coriolis. Everybody know what the Coriolis effect is? All right. So I didn't hear anything. There's several interpretations of the silence. I'll assume the most favorable to me. Huh?
When you have these, I don't know how to say, these streams of air that they're curving the Earth atmosphere.
That's an effect of it.
Yeah.
Well, what is it?
Well, I guess some cross product between.
All right. Let me break it down to baseball. Okay. So suppose I'm at the equator. Okay, and I throw a ball northward. Okay. I have a component of motion of the ball because I throw it, but I'm also going around this way because the Earth is rotating. Right? I have a certain angular velocity, a speed in this direction. I throw it up north. Let's say I throw it halfway up to the pole. Strong. Okay. The person up there is going around also, but slower, because he or she doesn't have as far to go. So as that ball goes up towards that person, it's got a component of velocity in this direction and a component in this direction, which is more than that person's component. And so from that person's point of view, the ball goes this way. Okay? That's the Coriolis effect. I'm not sure I call it a force. I call it effect. Okay. So everybody get that? Okay, so here is a little drawing. You throw a ball north, and it appears to go this way. This has a lot of practical applications. It turns out that rivers in the northern and southern hemisphere tend to be eroded more on one bank than the other because of the Coriolis force pushing the water that way. In space, the astronauts face this, they're weightless up there, and if they try to go outside the space station and do some repair, and they have a screwdriver, turn of these, and they want to go like this to turn some screw, their arm goes like that. And they have to train to compensate for that. I've talked to some of the astronauts, it's one of the most difficult things they have to deal with. If you look at Africa and South America, they used to be joined as one continent, and they've drifted apart. You cannot get their current positions just by pulling them apart. You have to rotate them. And I think that's a Coriolis effect as well. But that's a little bit controversial. Anyway, Coriolis effect, there it is. In terms of the orbits, notice that it corresponds to a tilting of the orbit axis. Instead of the orbit being this way, it's this way. So that's going to correspond in the Nielsen picture to a change in K. So the Coriolis force in the Nielsen model will mix different K values. Okay, here's the formal derivation of it. So we have a Hamiltonian for rotational motion, h bar squared over 2I.
Wait,
Yeah?
that argument didn't sink in for me.
Which one?
If you're standing on this side of the ball, then yeah, maybe the axis looks like it's that way, but on the other side of the ball, it's going to be pointing in a different direction.
It's always, if you're throwing north in the northern hemisphere, the ball's always going to go to the right.
Yes. Okay.
Okay? Okay, so let's just look at this Hamiltonian. In a deformed nucleus, there are two components of the angular momentum. Here's the total angular momentum. There's R and there's J. And so if I look at this rotational Hamiltonian, I have h bar squared over 2ij minus j squared. I can expand that, and then you all know this, so I'm not going to spend a lot of time on it. You can rewrite this using these raising and lowering operators and write j dot j as j1, j1, j2, j2, j3, j3, which you can then write in terms of these as 1/2 j plus j minus j minus j plus j3, j3. And so you now put that into here, and you get j squared, which is that, little j squared, which is that, this j3 term, which is that, and this term, which is that. Okay? And now going one step further, then the energies will be h bar squared over 2I. This gives j times j plus 1. This gives 2k squared, because those are the z components of the particle angular momentum and the little j, and those z components are the same. And then the matrix element of j squared. I'm not writing that as j plus 1 because in the Nielsen model those j's are mixed, but in any case it's a number. And then this operator. This is called the Coriolis matrix element because it corresponds to a tilting of the axis. And what it does is it mixes states that differ by 1 in k. Okay, so the Coriolis effect in a deformed odd mass nucleus will mix Nielsen orbits that differ by 1 in k. The matrix elements of j plus j minus are given by these familiar square roots. You all know those. Matrix elements of little j minus j plus are given by this. If you remember, Mark Caprio talked about a strange definition of why it's the opposite way, and I've never understood that, but it doesn't matter. Now, j is not a good quantum number. The deformed field mixes j values. So, big J, the total angular momentum, is just a number for a given spin state. Little j depends on the Nielsen wave functions. Nielsen wave functions are written as an expansion in Cj coefficients over the independent particle model wave functions. And so the matrix elements of j minus are given by a sum over Cj of orbit k, Cj of orbit k plus 1, those are the two that mix, times this square root of j minus k, j plus k plus 1. Okay? Okay, so the total, let me go back, the total Coriolis matrix element is then h minus h bar squared over 2I, the matrix element of big J, which is just that square root, the matrix elements of little j, which I repeat here, and then there's a pairing factor which comes in, and Augusto yesterday talked about these U and V factors, and they affect the matrix element because the particles are really quasi-particles, they're only partly in each orbit. And I'm not going to discuss this in great detail. In practice, you can take this number roughly as 0.7. It would vary from 0 to 1. And it's important in real calculations, but it's not important conceptually for what we're talking about. Now, I want you to notice the general form of this. Let's consider a fairly high spin state, where J is much greater than K. So this would be a high state in the rotational band. This square root is then the square root of J squared approximately, so it goes as J. Okay? This also goes as J. Okay? So if J is much greater than K. So the Coriolis matrix element, at least the maximum values, are going to be h bar squared over 2I times J times J. So that tells you that the Coriolis mixing increases with spin, and it can be a big number. This quantity is, you can approximate as the energy of the first 2 plus state in the neighboring even nucleus divided by 6. So if you have a 2 plus state at 100 kilovolts, that's 16. And if you're talking about a total angular momentum state, let's say of 15 halves, 7.5, that's 16 times 7.5, which is 120 kilovolts or so. And J might be 5 halves or so. So you can talk about matrix elements of maybe 200 kilovolts, 300 kilovolts. Okay, that's big, because if I go back to the Nielsen diagram, these energy spacings are on the order of 50 or 100, 200 kilovolts. So these are Coriolis mixing matrix elements that can be, at a maximum level, comparable to the spacings. So it can be a big effect. It often isn't, but it can be. Yes?
So now you're talking about state mixing between states with different J's?
I'm talking about mixing with different Ks.
Different Ks?
Yeah.
So Ks is already not a good quantum number.
Now it is not. That's why in a very early slide I said that K is a good quantum number for a Nielsen orbit, but that doesn't include residual interactions, and this is in a sense a residual interaction, which has the effect of mixing K values. Okay? All right. So the Coriolis force mixes states that differ in K by 1. Here's an example. We saw this already. We discussed these two orbits. 5 has minus 512. 7 has minus 503. So they differ by 1 in K, and so they will mix. Now, how big is the mixing matrix element? Well, this afternoon you're actually going to calculate one of them, but I'll give you some guidelines. The largest Coriolis mixing matrix elements occur if the change between these two orbits, delta and z, is the opposite of the change in lambda and is 1. So this is a case where there's a big Coriolis matrix element. So nz goes down by 1 and, yeah, that's right. nz goes down by 1 and lambda goes up by 1. So, I mean, it just turns out that way if you look at the Nielsen wave functions. So those matrix elements are on the order of 2 or 3. And all the cases of the unique parity orbit have matrix elements on the order of 6. And they all satisfy this rule. 660 mixes with 651, so 6 is going to 5 and 0 is going to 1. 651 mixes with 642, 5 is going to 4, 1 is going to 2, and so on. And the matrix elements involving the unique parity orbit are always the largest, and you can see that right here. Let's look at this matrix element for the unique parity orbit. Unique parity orbit, that's this orbit, I13 halves. Remember, these lines are straight. There's nothing, it doesn't mix with anything. Its wave function is nearly pure I13 halves. Right? All these others are quite highly mixed. But this one is pure. So now if we go to this expression, there's only one term in the sum, namely the highest K value. Okay? And so that's going to be 1. And then you're going to have a quantity here, which will be, if you just put in some numbers, you'll see that it comes out to be approximately n, the oscillator quantum number. So for the unique parity orbit, the Coriolis matrix element's on the order of 6. Here's an example where it would be smaller. 5 has 512, I took the same examples there. 7 has 514. Here n sub z is the same, and lambda differs by 2. That turns out to be a smaller matrix element. You'll see this when you see the table of the results. This is just a guideline, so in your head, you can estimate if you're gonna have big or small effects. Here is a table of theoretical values of J minus, and you can see here different orbits, and their numbers filled in whenever k differs by 1. So here you have, for example, 5 has 512, 7 has 503, so n sub z drops by 1, and lambda increases by 1, and you get 2.8. Here's a case, 1 half 510, 3 has 512, so that violates that rule, and it's on the order of 1. Okay? And this one you're going to calculate in one of the exercises. Okay, the Coriolis matrix element between these two. Actually, it's an optional exercise, but it takes you about 3 minutes. Okay? And for the UPO, the unique parity orbital, these numbers are typically about 6. Let's look at how big an effect this can be totally. We looked at the maximum values. Let's just do it again. So, h bar squared over 2I, we can approximate by the 2 plus energy in the even nucleus divided by 6. This matrix element is given by this. This matrix element is given by that, and we have a pairing factor. So typically in the rare earth region, the 2 plus energies are on the order of 190 or 100 kilovolts. So that divided by 6 is 15. This, if you plug in, say, J equals 5 halves and K equals 1 half, these numbers, these square roots are going to be on the order of 2 to 3. J minus matrix elements will be N, so that would be 6 for this region for the unique parity orbit, 1 to 3 for the others, and less than 1. 1 to 3 for these ones that satisfy this condition, and less than 1 for the others. The pairing factor, I'm not going to discuss that, approximated by 0.7. So the total matrix element is about 40. 40 is 15 times 2 to 3, times 0.7 for the pairing factor. And historically, people have found that if you do Coriolis mixing calculations with the matrix element you would calculate this way, you overestimate the effects. And so for, just as an ad hoc thing, they put in an extra attenuation factor, which is roughly 0.7. A lot of discussion of the origin of that. And then the J minus matrix element ranges from 0 to N. So if you multiply these out, you get 40 times 0.7 times 0.7 is 20. 20 times 0 is 0. 20 times 6 is about 150 kilovolts. So it can range from a few kilovolts up to hundreds of kilovolts. And so it can either have a very small effect or a pretty significant effect. Okay, there are 2 major effects of the Coriolis force. One is a diagonal effect on energies, and the other is an off-diagonal effect in terms of mixing of the wave functions. And so first I want to talk about a special diagonal effect. So there's an effect on from mixing. The levels will repel each other. But there's a very special effect that occurs in one particular case. Remember, and I'm not sure who showed this first, but in a deformed nucleus you have to write the wave functions in a symmetrized way, because the particle can go around the nucleus either way. And so if it's going around the nucleus this way, it'll have plus k. If it's going around the orbit in that way, it'll have minus k. We can't distinguish those. And so you write the wave function as a D matrix times a Nielsen wave function plus a phase factor times a D matrix with minus k, an intrinsic wave function with minus k. So you have both terms. That just corresponds to going around the nucleus in the 2 different ways. Now here's, yes?
Isn't wave function like the Nielsen wave function already deformed?
Yes.
So why don't we use just this wave function?
Oh, this is rotation. You have to add in rotation, because the nucleus can then rotate in space. The Nielsen wave function is in the body fixed frame. Okay. So now, there's something special that happens for k equals a half. Notice if you put k equals a half here, then you have minus a half here. K equals plus a half and k equals minus a half differ by 1. So the Coriolis effect can mix this wave function with itself. Okay? And so you get a self-mixing effect. If you go through the formalism, that gives an extra term in the energies. So here's what you'd normally get, just a rotational band. But now you get an extra term, which has an oscillating phase factor, and a quantity called A, which is given in terms of CJ coefficients like this. A is called the decoupling parameter for reasons that I don't want to go into. But anyway, it's an effect on the energies of the rotational band that oscillates with spin. And that phase factor ultimately comes from that phase factor and from mixing of the left-hand side with the right-hand side of the wave function in the matrix element. Okay? And so that's going, this alternating spin is going to lead to a sequence of rotational energies that don't follow JJ plus 1, but follow JJ plus 1 with an added alternating staggering. Okay? And you can forget this, that's just a numerical example. This is a little diagram of the rotational energies of a nucleus as a function of A. Suppose A is 0, that means no Coriolis mixing. Then I would have 1/2, 3/2, 5/2, 7/2, 9/2, 11/2, following pure J times J plus 1 sequences. Once I have a finite A, these energies will change, and they will change in opposite directions. The 1/2 will go up, the 3/2, the 1/2 will go down, the 3/2 will go up, the 5/2 will go down, the 7/2 will go up, 9/2 down, 11/2 up. If A is greater than 1, you actually invert the order. So you can get rotational bands where the order of the states is not monotonic in J. If you have an A value a little less than 1, say here, you'll get a 1/2, and then a 3/2 and 5/2 very close, and a 7/2 and 9/2 very close. And that's the effect you noticed earlier in a terbium 171, where you asked me about the energies of the K equals 1/2 orbit. Okay, and this is a figure I showed before, and I said that you'll see this later. So that is the 1/2, 5, 2, 1 orbit in erbium, and you get this sequence, 1/2, 3/2, 5/2, 7/2, 9/2, and so on. So the Coriolis effect leads to this special staggering, and if you remember back to 171 YB, you saw exactly that effect. Okay? So let's look at a realistic example of Coriolis mixing. And this example also, in a way, highlights the whole beauty and power of the Nielsen model. Here's the level scheme for dysprosium 161. Okay, I'd like you all to interpret this. Okay, you need some more information. You need the spins and parities, which I didn't have space to write. But if I wrote the spins and parities, and you look at the Nielsen model, and you know roughly the deformation, 0.25, 0.3, you can just count the number of particles and get where the last particle is, last neutron, and figure out what Nielsen orbits it goes into. And with a little bit of work, you can take all of these levels, and the work is not big. I mean, it's 20 minutes or so. You can assign them to all these rotational bands. There are a few here that are in trouble, but okay. Okay, you got a 5S542 with its rotational band. Got all these. Here's a K equals a half band with a decoupling parameter. Here's another one with a decoupling parameter of the opposite sign. Okay, so that's an interpretation of all of those levels, almost all of them, in dysprosium 161, just from the Nielsen model. Now, what about Coriolis mixing? So, here we have Coriolis mixing. The light blue ones are going to be cases where the mixing is relatively small. 5S523 with 3S521. That doesn't satisfy this delta NZ equals minus delta lambda equals 1 rule. Okay, here's another one, 3S521 with 1/2 521. Here's another one, you can follow them. The ones in red will be larger mixing matrix elements because they satisfy this rule. This one here is 5S523 with 3S532. So N sub Z and lambda go in opposite directions, and you have a couple of others. Okay, and you can put in and do a Coriolis mixing calculation. It's almost always safe to do it as a sequence of two-state mixings. In principle, you should do multi-state mixing because this will mix with this, which in turn will mix with this. But it's a very good approximation usually, except for unique parity orbits, to do it as two-state mixing. Okay? And remember, this k equals a half to k equals a half, that's the green one. And how much time do I have? Oh, I got time. Okay, I want to show you one of the mysterious aspects of rotational motion in odd A nuclei. So we all know what a rotor looks like, right? We have a nucleus, prolate deformed nucleus, which rotates, and as we go up the rotational band, it rotates faster and faster and faster and faster, right? Who sits at that corner of that table right there, the first table where you're sitting now? Who sits there? Yeah, you rotate your pen in your fingers. Could you demonstrate that? Okay, he does that all day. So that's a rotational nucleus, rotating faster and faster as you go up the rotational band, right? Right?
Yeah.
Wrong.
No, it is symmetry axis.
I want to, huh? Oh, I thought you said something. So I want to show you why that picture is completely wrong in an odd mass nucleus. Okay. As somebody over there asked, J is not a good quantum number. Okay, we've mixed J's. But angular momentum has to be a good quantum number. So there's got to be some other quantum number, some other angular momentum quantum number. And what it is rotation. So somehow the vector sum of J and R has to be conserved. Right? Okay, and so when we transform to the lab system, remember the Nielsen model is in the body fixed system, somehow we have to conserve J. Okay? Now, the normal picture I've drawn is this. We have a single particle angular momentum and a rotational angular momentum like this, giving a J value. But this is actually wrong. Okay? Because I fixed the positions of these, but actually this can precess around this way. Okay? And I want to take a look at that a little quantitatively. And what I'm going to do that is I'm going to look from this end. Look at the nucleus this way. And look at these vectors. This next picture, it's a little complicated, but I think you'll see the point. Well, that was good. Okay, well, actually, let me introduce it a little first. Think of a band built on the 3s651 orbit. Just think about this. This is from the unique parity orbit. Okay, so it has nearly pure J equals 13 halves. It's one of those straight orbits. Doesn't mix with anything else. Okay, so it's almost pure J equals 13 halves. Now think about the J equals 5 halves state of this rotational band. So we have 3 halves, 5 halves, 7 halves, 9 halves. Think of the 5 halves. And think about the fact that the intrinsic Nielsen wave function is almost pure 13 halves. So if the only single particle angular momentum is 13 halves, how do we make a 5 half state? We need to have a rotation, a negative rotational angular momentum of 4 units to connect 5 halves and 13 halves. Okay? Clear? Right?
Sorry, again.
Let's look at the 3s651 orbit. So we will have a level scheme for that orbit, which will look like three has plus, 5 has plus, 7 has plus, 9 has plus, and so on. And they will follow a beautiful J times J plus 1 energy spacing. We've seen many examples of this, right? But now I want you to analyze it a little more in detail. This is the 3 halves 651 orbit. It comes from the I13 halves single particle orbit. That I13 halves is the unique parity orbit. It's the only orbit in that shell with positive parity. So its wave functions in the Nielsen picture are almost pure, and they're dominated by CJ, by J of 13 halves. So the CJ coefficient is 13 halves, is 1. Okay, so if I have a single particle with pretty good angular momentum 13s plus, and I want to make a 5s plus state, the other angular momentum I need is a rotational angular momentum of r equals 4 going down. I'm opposing that 13 halves. Clear? Okay, now let's look at the 13 half state of the band. So up here somewhere there'll be a 13 halves. Now I have a particle with single particle angular momentum 13 halves. I don't need any rotational angular momentum. Right?
So mathematically it's clear, but physically, what is this R for?
You'll see in a second.
So you want to say that in this picture, the nuclei is rotating slower and slower and slower when we go up the bend, not faster and faster and faster?
That's the question I'm posing. So you would think that this would be rotating less than this. And therefore this should have the quantum numbers of all the n equals 5 orbits. You have to remember about this one down below. And so you just start with the fact that the lowest orbit is going to have the highest n sub z. It's going to be an equatorial orbit around the nucleus close to the nuclear matter. And so the quantum number there will be 5 for n. It'll be 1/2 for k because it's an orbit like this. The nz quantum number, which is the most important, will be 5. In other words, the maximum value. And then lambda differs from the k by 1/2. It just differs by the nucleon spin. And so if this is 1/2, the lambda has to be either 0 or 1. If this is 3 halves, it has to be 1 or 2. And the way you figure out what it is n sub z plus lambda has to have the same oddness or evenness as n. So if this is n equals 5 and nz is 5, I have a choice of 0 or 1. For lambda, it has to be 0. Okay, and then you just march up. You can either march up within a single particle level or march up with all the 1/2 levels. Do it either way, okay? And I think you all pretty much got that with maybe a little confusion from time to time. And so then I asked you to label these quantum numbers and do an actual calculation and look at the wave functions. And the only comment I want to make is that many of you kept looking, let's say, at an orbit like this and saying it's an f7 halves orbit and thinking in terms of f7 halves. Don't do that. Think of the Nielsen diagram as a separate calculation for each epsilon. Think of it in terms of these wave functions. If you think of it in terms of the parent single particle states, you will get confused.
Yes.
Because this one, for example, is mostly H9 halves because it's past the crossing point. One way you can do it is take a scale and go like that, and it'll point toward the one whose wave function is the largest component. All right, so this just says, think of the Nielsen model, don't think so much of the spherical parents. Okay, I got a very interesting question from someone, the back table, I think there. They were looking at this wave function 7s514, and lambda is the projection of the orbital angular momentum on the symmetry axis, and they asked how can it have these j values. This is odd parity, so that's p a half, p a half, p3 halves, f5 halves, f7 halves, and so on. How can you have a projection of 4 and yet have a component with L equals 3? Okay, because f7 halves, f is L equals 3. So how can you have that component when the wave function has a projection of 4 on the symmetry axis for the orbital angular momentum? And that stopped me for a while, and then I realized these are asymptotic quantum numbers. They apply in the limit of large deformation. And it's an approximation to use them anywhere else. And so I did a calculation last night where I took, instead of delta equals 0.2 or epsilon equals 0.2, I took epsilon equals 0.6, and then you see this component is dropping rapidly. And if you go to epsilon equals 3,848, it'll be almost 0. Or some other large number. Okay. So, this exercise, you all did pretty well. The one huge mistake you all made, whoops. Oh, I'm sorry, I have these out of order. The next thing was to, I'm sorry. Next thing was to analyze 183 tungsten. And we did pretty well there. I just want to make a couple of comments on that. Okay, this is the experimental level scheme, and I've just color-coded some things. So if you counted right, you should have gotten, I know these can't be read, but that was actually semi-intentional. I mean, it's not intentional. I discovered they couldn't be read, and then I thought, that's good, because they should be able to figure them out. But in any case, this is 7s503, and most of you got that that should be the ground state, whereas the ground state's actually this. And the reason for that has to do with hexadecibel deformations. I just wanted you to see that the model doesn't always work. But in any case, these three orbits here that are clustered right together, where this is the ground state, correspond to these three, which are at pretty low line energies. And then, and this one, this 7s503, is up higher than you would expect because of the hexadecibel deformation. And then you have these three, what you could call hole orbits, down here. These four, I mean, 1, 2, 3, 4, 1, 2, 3, 4, which are all clustered there. And that's basically the level scheme you get. Somebody made the comment that, so you can get the excitation energies of these by just taking the differences in these energies, and you know the scale over there, so you should be able to calculate excitation energies. And somebody made the comment that they were getting excitation energies which were closer together than you would predict from the Nielsen model. And I thought that was an interesting comment. And there's a reason, and Augusto talked about part of this yesterday, and I don't know if you're going to talk about the other part today, but I'll give you a quick answer. He talked about the development of the pairing gap in even nuclei. When you have pairing, ground state comes down very low, there are very few states here, and then suddenly a huge number of states. Due to pairing, there's this energy gap, right? That's for even nuclei. The opposite happens for odd nuclei. The low line levels are compressed. And maybe he'll talk about it, and the reason why is up there if you care to look. But in any case, in odd mass nuclei, the low line levels are actually squeezed. And so in the Nielsen model, when you look at the actual energies compared to the predicted energies, you'll find they're closer to the ground state. This, one second, this has a consequence. As you go across a series of nuclei, series of isotopes, you would generally expect a given Nielsen orbit to go as you go through a series of isotopes and add neutrons, you would expect a given orbit to go from high energy, say you're filled up to here, and then you put two more nucleons in, it goes lower energy, lower energy, lower energy. You'd expect it to go like that, and cross zero when you're filled up to that orbit, and then be a whole state. But because of this compression, it doesn't quite look like that. And what you see is this. This is data. This is systematics of the energies of these orbitals. This is zero. This is where they would cross the Fermi surface. And what you see is they tend to flatten out here. And that's actually an effective pairing. And I think Augusto may talk more about that. You had a question?
Yeah. So can you just maybe talk about why it makes sense that odd nuclei get compressed?
Okay, I don't want to do Augusto's talk, and he'll do it better than I will, but I'll give you the reason quickly.
No, I mean, we look at this in the activity, but you can explain it.
All right, well,
I'm not going to.
So there's a concept of a quasi-particle. Instead of, and you talked about that yesterday.
Yeah, that day.
So instead of having just an energy epsilon for a single particle state, you have a quantity square root of epsilon minus lambda squared plus delta squared, where that's the gap. In an even nucleus, to make an excited state, you have to create two particles, two quasi-particles. And so the energy is going to be one of these square roots plus the other. Okay, the minimum value for that is 2 delta. Right? The minimum this can ever be, this square root is delta. The minimum this can ever be is delta. So the minimum is 2 delta. When you have an odd mass nucleus, you take a particle from one orbit to another, you replace one of these by another, so it's a difference. Okay? And let's imagine that this one here corresponds to the particle at the Fermi surface, so epsilon minus lambda is 0. You can write this as square root of epsilon minus lambda squared plus delta squared minus delta. And if you just plug in numbers for this, you'll see that if this is significantly smaller than delta, in other words, if you're talking about the low-lying levels, you'll just get a compression. Okay, it's because you're replacing one quasi-particle by another rather than creating two of them. It's actually not very well known, that effect. Okay, now, the one major mistake you all made was to draw the 11 halves as coming down, whereas I told you it was going up. And then some of you did a calculation, you found out that it goes down. And so I have to deeply apologize. And I said I would go back and find out the reason. I found out the reason. You remember I showed this table of the angles of these orbits as a function of k. If you look at 11 halves, it's 58 degrees. And 58 degrees is something like this. And that's actually in a region where, due to the hexadecimal deformation, the nuclear matter is even closer to that orbit than it would be without it. Whereas I just, in my mind, was thinking more like this, being further apart, and so I just had an intelligence gap. So it actually comes down slightly. And these are the calculated values, so you see this compression of levels. This has a humongous effect on practical spectra, and the reason is that these orbits, if you remember, these orbits from the unique parity orbit have quantum numbers 1 half 660, 3 half 651, 5 half 642, 7 half 633. Delta n sub z is changing by 1, it's going down, and lambda is changing by 1, it's going up. And so that's the maximum Coriolis matrix element. And these Coriolis matrix elements between these orbits, they all mix, are on the order of hundreds of kilovolts. If you look back at the slides from yesterday, Janelle, on the web, you'll see an estimate of 150 kilovolts or so. And so if you have a nucleus with a large hexadecal deformation, you get tremendous Coriolis mixing. Okay? I think I'm done, but let me just check. No, there was nothing here. Somebody said they got a number for this, which was 1.12 or something. If you take the output you get, that output actually prints out these matrix elements. I don't know if you ever noticed it. That output is 1.146. And so I probably calculated this with slightly different parameters, but it doesn't matter. Okay, any questions? Okay.